Hello everyone and welcome to this new presentation or training in Calculus ODE or Ordinary Differential Equations. So we're going to see different types of differential equations, multiple orders, first order, second order, and let's check what we have in the menu. So as an intro, we're going to introduce which order and degree or what is the definition of an order and degree for a differential equation, the general and particular solutions, first order differential equations, the types of it, separable, linear, exact, and Bernoulli, and how to solve each one of them. Then second and higher order equations or differential equations, homogeneous, non-homogeneous, systems of first order linear ODEs, series solutions of ODEs, how to solve an ODE using power series, Laplace transforms, and finally qualitative analysis of nonlinear systems. Starting with definition. So what is a differential equation? A differential equation relates a function with its derivative or derivatives, because at times you have multiple derivatives, that describes, if it is singular, a change of that function in respect of time or another parameter. Types, you have ordinary differential equation, ODE. It involves a derivative in respect to one independent variable. Example, dy over dx plus y equal ex. And of course you have other types that involve multiple dependent parameters. That type would be called partial differential equations or PDE. It involves derivatives to multiple independent variables simultaneously. Example, du or partial u over partial t, which is the derivative of u in respect of t, is equal to d of d square u divided by du square. Order and degree. The order is the highest level of derivation within the equation, i.e. first, second, third derivative, respectively, of course. So d to the third order of y divided by dx3, meaning that this is the derivative of y in respect of x to the third order, the third derivative, plus 2d square y over dx square minus y equals 0. So this is an ODE differential equation of the third order, which means that the highest derivative is the third derivative, which is d3y. Of course, we also say it partial y to the order of 3, but I'm saying d to make it more brief. As for the degree is the power of the highest order derivative. Okay, not the derivation level, but the power. So it is raised to the power of 2, 3, etc. Or multiplied by itself by how many times? This is what we mean by the degree. So d3y over dx to the power of 2, okay, plus 2 dy over dx to the power of 4 is equal to 0. This is the third order, second degree ODE. Okay, why? Because the highest derivative, which is d3y over dx, has the power of 2, so it is the third order derivative of second degree y, because the power of the highest order derivative is 2. That's why it is of the second degree and third order. A general solution for an ODE is one that contains all possibilities through a generic equation without any specific final result. It has a dependency on a constant c, where c is undetermined or to be determined. This solution is the outcome of solving the differential equation without initial conditions. Actually, when we have initial conditions, you can get to find the c or the c's. You can have multiple constants within the solution. So let's say you have dy over dx equal 3x squared. That's a form of a differential equation. You have the derivative. You need to find y, which is the solution. So you integrate both sides in this simple example, integral of dy over dx is equal to integral 3x squared. So you multiply the x by 3x squared, you get integral of dy is equal integral of 3x squared dx. Now, the integration of a derivative gives us the function, simply. So, int of dy or integral of dy is simply y, and integral of 3x squared dx, you notice that we multiplied 3x squared by dx, which is in the denominator here. We multiplied the extremes, so it gives us 3x to the power of 3 over 3, or x3 plus c. Of course, don't forget the constant, which is the constant of integration. A particular solution represents a special case in the general solution. While the general one has an infinity of curves that change in respect of c, which is the constant, when plotted, a particular solution will have only one curve because of finding the value of c for that case or condition. So y equals 3x to the power of 3 divided by 3 plus c equal x3 plus c. Let's suppose for x equal 2, y equal 12, or y of 2 equal 12. Then we replace the values of y and x in the equation, y equal x3 plus c, that's the equation we're talking about. We get 12 equal 8 plus c, which means that c is equal to 4. We place it back in the general equation, y equal x3 plus c, then this becomes the particular solution for that condition, y, which is y2 equal 12. Y equal x3 plus 4, that's the particular solution. In conclusion, the general solution contains an undefined constant with unlimited possible curves and without an initial condition. As for particular solutions, they have an initial condition and one specific curve with no constants within the equation. For a second order ODE, you get more than one constant. Example, y of x is equal c1 cosine x plus c2 sine x. Initial conditions, y of 0 is equal to 1 and y prime of 0 equal to 0. The second initial condition pertains to the derivative of y of x, not y of x. So we need to solve the derivative. Y prime of x is equal to minus c1 sine x plus c2 cosine x. So y of 0 equal to 1, you fill x and y in the first equation. Then y equal to c1 cosine 0, which is c1 plus 0, then c1 is equal to 1. Y prime of 0 equals 0, you fill it in the derivative or second equation. Then 0 equal c2 cosine 0, because the first component is 0. So c2 is equal to 0. You fill back these values within the first equation, and you get this particular solution, y of x is equal to cosine x. Direction fields and qualitative behavior. A directional field is used to visualize the solutions of a first-order differential equation. It is also called the slope field, since the first-order derivative represents the slope of a function, or tan alpha, or how much a function is slanted. So let's say we have a function dy over dx is equal to fxy. dy over dx, or the slope for this function, will have a different value for each unique xy point. As a reminder, the slope is equal to the rise over tread, which represents the inclination of the tangent against this function. S equal, or slope equal, rise over tread. Direction fields are essential in understanding the behavior of a solution, whether it grows, decays, or decreases, or stabilizes in progression of its parameters, x and y in this case, which can be space and time parameters. This also can tell us where the function stabilizes, which is when dy over dx is equal to 0. Qualitative behavior, this leads us to understanding the progression and trend of the solutions, without having necessarily to find a particular solution. The key aspects to look for are equilibrium. The state of equilibrium is the points or the solutions when dy over dx is equal to 0, stability, and behavior over time. So let's talk about equilibrium. This is where the function becomes leveled and no longer is changing up or down like a horizontal line. Actually, the slope of the tangent over that function in that area becomes 0, or tan alpha is 0. In other words, dy over dx is equal to 0. Example, find the equilibrium in the following function. Of course, you can try to find out yourself. Dy over dx is equal to y times 1 minus y. Okay, let's solve it for dy over dx is equal to 0. You place y times 1 minus y is equal to 0, and you solve it for y, and you get these two solutions, y equals 0 and y equal 1. So equilibrium is reached at these two points, y equals 0 and y equal 1, which are the solutions for this equation. Stability. A solution is stable when the other solutions surrounding it converge, or in other words, move in its direction. It is unstable when they move away or diverge. Behavior over time, it describes where the solution goes at infinity, whether a constant value or an asymptote. And it can also, the function, go to infinity as well. For the following differential equation, dy over dx is equal to x minus y, compute the slope at the following points. You can try at this exercise yourself before moving on. 0, 0, 1, 0, etc. Okay, so this is the slope of the function. Dy over dx is the slope, or the tangent tan alpha against the function, against the curves. We simply fill in 0, 0, 1, 0, the different points in x and y within dy over dx. So you get, for 0, 0, dy over dx is equal to 0. It's not changing. For 1, 0, it is 1. For 0, 1, it is minus 1. It's going down. Here it is going upward. And here it stabilizes again at 0. It is an equilibrium in order to be more accurate. For 2, 1, it is 1. For 1, 2, it is minus 1. For minus 1, 0, it is minus 1. So decrease, increase, and finally also increase. For 0, minus 1, it is 1. At first, you start drawing the different points. So 0, 0, 1, 0, 1, 1, etc., 2, 1 on the graph. Then for the slopes, you look at the slopes. So what you have here is 0, 1, minus 1. For example, for 1, 0, the slope is 1. Okay, 1, 0 is, this is 1, 0, 1 over x, and 0 over y. So what would be the slope? Minus 1, which means it is going downwards this way. Okay, remember, the slope is rise over tread. This is the rise and this is the tread, but it is inverted. Okay, for example, for 1, 0, it is plus 1. This is 1, 0. That's the point. Plus 1 means it is rising of 1 square, each one square headed in the horizontal direction. Okay, and as you notice, if we plot the function itself, these are the tangents to the different curves within the function. Another example for minus 1, 0, 0, minus 1, it is minus 1. Okay, so this is minus 0, it is minus 1. What does it mean? It means that it's going downward. It goes from 1 to 0, or like from a higher level to a lower level. When it's 1, it is pointed upwards, which means it has a 90-degree difference with its counterpart. Okay, so for instance, for 2, 1, it is plus 1. And here it's obvious. For each square we go to the right, it's going upward 1 square. This is how it works. Exercise for the following differential equation, dy over dx is equal to x minus y. Find the qualitative behavior. At first, of course, you can try to solve it yourself and then come back to the video. So you solve it for dy over dx is equal to 0. What we get is y equal x, which means that as x goes to infinity, most solutions tend to y equal x. Okay, so the slope is horizontal and the function is neither going up or down near this line. It's not horizontal per se but it follows through that line, which is y equal to x. For y greater than x, dy over dx is less than 0. Okay? Why? Because dy over dx becomes negative if y is greater than x. So above this line, the solutions curve downwards. For y less than x, dy over dx becomes greater than 0. Why? Because simply x is positive and y is negative. When y is less than x, dy over dx is greater than 0. Which means below this line, the solutions curve upwards below y. Okay? Y equal x acts like a stable equilibrium line to which all solutions bend over time. Another exercise, try to solve it yourself, of course. Find the qualitative behavior of dy over dt equal y times 1 minus y. You can pause the video and try to solve it. Alright, so at first we solve the equation for dy over dt equal to 0 to find the equilibrium points. If dy over dt is equal to 0, then you simply get y equals 0 and y equal 1 plus 1 as solutions. These are the equilibrium points. So now dy over dt can also be rewritten as y minus y squared. So this is a second degree equation. You can solve it for y minus y squared equal to 0. For y is between 0 and 1, which are the solutions in such case, since the argument multiplying y squared is negative, then between the two roots, all solutions are positive, okay? So between 0 and 1, y, or for y is between 0 and 1, dy over dt is positive, so y increases. Now, outside of that domain, so if y is greater than 1 or y is less than 0, then dy over dt is negative, less than 0. Then in such case, y decreases. Another exercise, find the qualitative behavior of dy over dt is equal to y plus 1 times 3 minus y. Of course, you can pause the video and try to solve it yourself. Going back to the video, so let's solve the second part of the equation, which is y plus 1 times 3 minus y, to find the equilibrium points. You simply place dy over dt is equal to 0 and you solve for y, the second part of the equation. We get y equal minus 1 and y equal 3. These are the equilibrium points. Now, going back to the expanded original form of the equation to the right, dy over dt is equal to minus y squared plus 2y plus 3. This is the form of a polynomial equation, which is ar squared plus br plus c is equal to 0. In such case, when a is negative or less than 0, then dy over dt is positive, is greater than 0 for r is between the two roots that we've just found. So for r is greater than r1, the first root, which is minus 1, and less than r2, which is plus 3, in such case, dy over dt is greater than 0. It is increasing. And it is negative or less than 0 otherwise. Or in other words, for r less than r1 and greater than r2. So for y between minus 1 and 3, minus 1 and 3 not included, dy over dt is greater than 0, then y is increasing. For y is less than minus 1 and greater than 3, so we flip the inequality of the upper line, dy over dt is less than 0 and y decreases. And this is the plot to the right of the function. Here are some takeaways that you need to remember. At first, direction field, it is a graphical representation of the slopes of solutions of a first order ODE or ordinary differential equation. Equilibrium solution, a horizontal solution line where dy over dx is equal to 0. Stability, it describes the behavior of nearby solutions if they approach or diverge. And qualitative behavior, the overall trend of solutions, whether they are increasing, decreasing, or stabilizing horizontally over time. First order differential equations. Separable equations, that's the first type. A separable equation is a type of first order ODE where you can separate the variables of the equation, i.e. moving the terms, with x to one side of the equality and the ones with y to the other side. An ODE is separable if it can be written as dy over dx is equal to fx gy. Assuming gy is different than 0, this can be written as 1 over gy dy equal fx dx. How to solve? We integrate on both sides and we try to find a solution for y if possible. Then we add a constant or two depending on the equation. So this is the form integral of 1 over gy dy is equal to integral fx dx. Example, solve the following. Dy over dx is equal to xy. You can try to solve it, and it's straightforward actually. We simply need to separate the variables, so you take x to one side and y to the other side, so we get dy over y equal x dx. And we need then to integrate both of them, so integral of dy over y is equal to integral x dx. dy over y, the integration gets us ln y, the logarithm of y. And integral of x dx is equal to x2 divided by 2 plus c, which is a constant. So ln y is equal to x2 over 2 plus c. Then y becomes the exponential of x2 over 2 plus c. Again, so to solve y in respect of x2 divided by 2 plus c, we need to elevate both sides of the equation to the exponential. This is how we can get rid of the ln. So e ln y is equal to e x2 divided by 2 plus c. Hence, you can get y, because e ln y is equal to y, is equal to e x2 divided by 2 plus c, which is e x2 divided by 2 times e to the power of c, which is a constant. So we can designate a, the constant of the integration, if you will, is equal to plus minus e to the power of c, and we multiply it by ex2 divided by 2. This is the solution y of x. Another important note, by the way, is to pay attention to the fact that e to the power of c is plus minus here, correct? A is equal to plus minus e to the power of c. This is due to the fact that y was an absolute value. So although we've gotten rid of the logarithm y in absolute value, it means that the values to the right can be either positive or negative. So for e to the power x2 divided by 2, we have no problem because we have x squared. It's always positive. As for e to the power of c, it can be either positive or negative. Another form of first order differential equations is the linear equations. This is a first order linear equation involving a function y of x and its first order derivative dy dx over dx without other higher order derivatives. The standard form is dy over dx plus p of x times y, so this is a function of x times y, equal q of x, which is to the right of the equality. P of x and q of x are known functions of x, y of x is the unknown. Now, how to solve this type of differential equations, which is the linear type? Again, you have dy over dx plus p of x, y is equal to q of x. This is the form. At first, you need to identify p of x and q of x. Find the integrating factor, which is mu of x is equal to e exponential to the power of integral px dx. Once we find mu of x, we multiply it throughout the equation from left to right. Then the left-hand side becomes a derivative of mu of x, y. And we will see how in the next example. So d of mu of x, y over dx is the equivalent of the left side of the equality that you see here, is equal to mu of x, q of x. After that, once we get it into this form, we need to solve for y. So y of x is equal to 1 over mu of x integral mu of x, q of x dx plus c, which is the constant of integration. Example. here things will clear out better for you within this equation. So dy over dx plus 2y is equal to x. First thing that we notice is that this equation is of a linear form, where we can identify both p of x and q of x. So the form is dy over dx plus p of xy equal q of x. So p of x is equal to, which is the component multiplied by y, and q of x is the one at the right side of the equation, which is x. Then we need to find the integration factor. So mu of x is equal to e exponential integral p of x dx equal e integral 2 dx, or 2x exponential of 2x. After that, we multiply both sides of the differential equation by mu of x, which is e to x. So e to x dy over dx plus 2y e to x is equal to x e to x. We notice based on uv prime, the law of the derivation of the product. Let's say you have two numbers u and v, or two quantities u and v. uv prime is equal to u prime v plus uv prime, which means the derivation of the first times the second plus the first times the derivation of the second. If you notice something, e to x times y prime, the derivation of these two, will give us 2e to x times y plus e to x times y prime, which is what? Another writing for dy over dx. So the derivative of e to x times y over dx gives you e to x y prime, which is dy over dx. Here we are rearranging this term, plus 2y e to x. So mu of x y, which is e to x y, the same term that we've seen before. We place it back in the first equation. So instead of e to x dy over dx plus 2y e to x, we flip it into the derivative of e to x y and equal to x e to x. So d e to x y over dx is equal to x e to x. Then we integrate both sides of the equation. So integral d e to x y over dx, which we multiply over the next side, integral x e to x dx plus c prime. Here you have two factors that are multiplied together, so we need to integrate by part. Let u equal to x, du is equal to 1, dv is equal to e to x, then v is equal 1 over 2 e to x. So integral u dv is equal to uv minus integral v du. So e to xy, which is the integral of the derivative, gives you e to xy, is equal to the integral of x e to x dx, which is 1/2 x e to x, minus integral v du, which is 1/2 e to x times 1, so 1/2 e to x dx plus c prime. Hence y is equal to 1/2 x minus 1 over 4 plus c prime over e to x plus c second over e to x. Okay, because you have c is equal to c prime plus c second. Hence y is equal to 1/2 x minus 1 over 4 plus c e to the power minus 2x, which is c prime plus c second. Okay, the same thing. As a wrap up, so at first we need to identify p of x and q of x, then the integration factor, which is mu of x is equal to e integral p of x dx equal e to x in this case. Then we multiply mu of x, the integration factor, by the entire equation. Then we identify d e to x y over dx, which is again the derivative of the two components e to x and y that got us u prime v plus uv prime form, which is e to x y, derivative of y or y prime, plus 2y e to x, which is y times derivative of e to x, which gives you 2e to x. So derivative of e to x y divided by dx is equal to integral x e to x dx plus c prime. The x, you multiply it to the right and we get rid of it actually to the left. So e to x y is equal to 1/2 x e to x minus 1 integral 1/2 e to x dx plus c prime, which is the integration by part. Hence, you get the solution y is equal to 1/2 x minus 1/4 plus c prime over e to x plus c second over e to x, which is c times e minus 2x, okay? C being c prime plus c second. Exercise dy over dx minus 2 over xy equal x squared. You can pause the video and try to solve it yourself. So the form of the linear equation is dy over dx plus p of x y equal q of x. Identifying p of x and q of x, p of x is equal to minus 2 over x, which is the quantity multiplied by y, and q of x is equal to x squared. So integration factor, mu of x is equal to e integral p of x dx equal e integral minus 2 over x dx, which is e minus 2 ln x, or e ln x to the power of minus 2, which is 1 over x squared. That is mu of x. Multiply by the integration factor mu of x left and right, so 1 over x squared dy over dx minus 1 over x squared 2 over x y equal 1 over x squared. Okay, so u is equal to 1 over x squared, v equal to y, uv prime is equal to u prime v plus uv prime. So y prime times 1 over x2, which is the derivative of y times 1 over x2 plus y derivative of 1 over x2, which is minus 2x over x squared, equal to dy over dx 1 over x squared. Dy over dx is y prime minus 2 divided by x3 y equal d of 1 over x squared y over dx, which is the derivative of 1x squared times y. We place it back in the equation, so you get d mu x y over dx is equal to 1. So d of 1 over x squared y over dx is equal to 1. We integrate on both sides of the equality. So integral d of 1 over x2 y divided by 1, because we multiplied the x to the next side, is equal to integral 1 times dx plus c is equal to x plus c. So 1 over x2y is equal to x plus c. Y is equal to x3 plus x2c. This is the general solution. Now let's find, for an initial condition y of 1 equal to 3, a particular solution. We simply replace x and y by 1 and 3 respectively. You get 3 equal, which is y, 1 to the power of 3 plus 1 square c, then c is equal to 2. So we replace 2 in c of the first solution, which is the general solution. Hence the particular solution becomes y is equal to x3 plus 2x squared. A new exercise, dy over dx plus 3y equal 6e minus 2x. And also finding the particular solution for y0 equal 6. Of course, you can pause the video before we get into it. So let's start. First, we identify p of x and q of x. P of x is 3, the quantity multiplied by y. Q of x is equal to 6e minus 2x. Let's find after that the integration factor. Mu of x is equal to e integral p of x dx equal e integral 3 dx, which is e3x. Then we multiply the entire equation by this factor. So e3x dy over dx plus 3y e3x equal 6ex, because this is the multiplication of e3x times e minus 2x. So what remains is ex times 6, of course. Okay, so u equal y, v equal e3x. uv prime, or the derivative of these two multiplied together, gives you u prime v plus uv prime, which is the quantity you see on the left or to the left of the equal sign. So dy e3x over dx is equal to y prime e3x plus 3y e3x. which is also what? It is dy over dx times e3x plus 3y e3x, which you have here to the right. Then it is equal to e3x dy over dx plus 3y e3x. So dy e3x over dx is equal to 6ex. This is what we have so far. We placed the q of x, which is multiplied by e3x, the right of the equation, next to dy e3x over dx. Then we integrate on both sides. So you have integral d of y e3x over dx equal integral 6ex. You multiply the x to the right, which are the extremes before and after the equal. And what you get is integral dy e3x is equal to integral 6ex dx plus c. Of course, the integral of the derivative gives you the function or what's within the derivative itself. So the general solution becomes y equals 6 divided by e2x plus c divided by e3x, because we multiplied e3x in the denominator of these two components. So y equal 6e minus 2x plus ce to the power minus 3x, because we elevated the exponential to the numerator. This is the general solution. Now we have the general solution. We need to find, based on the initial condition, the particular solution for this equation. So finding the solution for y0 equal to 6, you simply fill in the values of x and y, which are 0 and 6 respectively, within the general solution to get c. So you have 6 equal 6e0 plus ce0, then c equals 6 minus 6, which is 0. So the particular solution is y equals 6e to the power minus 2x. Another type of the first order differential equations is the exact equation. An exact first order differential equation is an equation that comes from the total derivative of a function of two variables, x and y. It has the form pxy dx plus qxy dy is equal to 0. An equation like the one above is called exact when there exists a function fxy such that df over dx is equal to pxy and df over dy, or derivative of f in respect of y, is equal to qxy. You have the partial sign because it is a partial derivative. To put it in a different way, the total differential should be 0, or df is equal to 0. And the solution fxy is equal to c, which is the constant of the integration. At first, we need to test for exactness. So for a differential equation to be exact, you need to have partial p over y, or derivative of pxy over y, should be equal to derivative of qxy over x. This is how you know that it complies with the exactness. How to solve exact differential equations? Given pxy dx plus qxy dy equal 0. At first, we need to check for exactness. So derivative of p in respect of y should be equal to derivative of q in respect of x. If they are equal, then the solution is for an exact differential equation. Okay, then you have an exact differential equation. Then integrate pxy in respect of x. So fxy is equal to integral pxy dx plus the constant is hy. It is an argument in respect of y, dependent on y. After that, we differentiate in respect of y and equate it to qxy to find hy. And finally, write the solution as fxy is equal to c. Example, 2xy plus 1 dx plus x squared plus 4y dy equal to 0. Of course, you can pause the video and try to solve it yourself. Now, before even checking for exactness, we need to identify p of x and q of x, which is straightforward because the part multiplied by the x is p and that by dy is q. Let's check for exactness. So, dp over dy, or derivative of p in respect of y, should be equal to that of q in respect of x. Derivative of p in respect of y, which is derivative of 2xy plus 1 in respect of y, is equal to 2x. Then derivative of q in respect of x is that of x2 plus 4y over dx, which is equal to 2x. Then the differential equation is exact. After that, we integrate p of xy in respect of x. So fxy is equal to integral of px or pxy in respect of x equal to 2x2 over 2 times y plus x plus hy, which is the third component, okay, in place of the constant. So equal x squared y plus x plus hy. After that, we need to find hy. To do that, we need to derive in respect of y and place it next to qxy. So derivative of the entire solution here, not solution, but fxy, in respect of y should be placed next to qxy. Let's derive in respect of y and place it equal to qxy. So d, or derivative of x squared y plus x plus hy over dy in respect of dy equal qxy, which gives us x squared plus 0, because this cancels out, plus h prime y, which is dh over dy, equal x squared plus 4y, which is qx. Then h prime y, which can be rewritten, dh over dy is equal to 4y. You multiply 4y by dy on this side, so you get dh equal 4y dy, and then we integrate both sides. So integral dh, which gives us h by the way, is equal to integral 4y dy. Then hy is equal to 2y squared, because 4y squared over 2 gives you 2y squared. Then you place it back in the original equation. So fxy is equal to x squared y plus x plus 2y squared, which is x squared y plus x plus 2y squared equal to c. That's the final solution, because remember fxy, you place it at the end, equal to c, which is the constant of integration. Exercise 3x squared plus 2y dx plus 2x plus 4y dy equal 0. You can pause the video, of course, and try to solve it. So at first, we need to check for exactness. As a reminder, this is p of x and this is q of x, the part multiplied by dx and dy respectively. So derivative of p of x over y is equal to 2, okay? Then derivative of q of x in respect of x gives us 2. So since both derivatives are equal, then the equation is exact. After that, we need to integrate p of x in respect of x. So fxy is equal to integral 3x squared plus 2y dx plus hy equal x3, which is 3x3 over 3, plus 2yx plus hy. After that, we need to derive in respect of y. Okay, derive in respect of y and place it equal to qxy. So the derivative in respect of y gives us, and this is q of x by the way, 2x plus h prime y is equal to 2x plus 4y. Then dh over dy, which is h prime y, the same thing, is equal to 4y, because 2x and 2x to the left and to the right cancel out. Then dh is equal to 4y dy, and we integrate both sides. Integral dh is equal to integral 4y dy. So we integrate and we get hy is equal to 2y squared. Then you place it back in the original fxy equation. So fxy is equal x3 plus 2yx plus hy, which is x3 plus 2yx plus 2y squared is equal to c. And of course, if we had an initial condition, we can easily find a particular solution, which is dependent on the value of C. Another exercise, 6xy plus 4dx plus 3x squared plus 2y dy. You can pause the video and try to solve it yourself. It should have become easy by now. So, p of x is the first part, q of x is the second part. We need to derive p of x in respect of y. This is checking for exactness again. It gives you 6x. Derivative of q of x in respect of x gives us also 6x. Then derivative of p in respect of y is equal to that of q in respect of x. So the solution or the equation is exact. fxy, let's derive p of x in respect of x is equal to integral 6xy plus 4dx plus hy, which is equal to 6x squared over 2 or 3x squared y plus 4x plus hy. After that, we need to derive the entire thing in respect of y and place it equal to q of x, which is 3x squared plus 2y. So derivative of this entire equation here, which is fxy in respect of y, equal 3x squared plus 2y. It gives us 3x squared, 4x cancels out, plus h prime y, which is dh over dy, is equal to 3x squared plus 2y. So we integrate both sides, of course, after multiplying dy to the next side. Integral dh, which is h, is equal to integral 2y dy, which is 2y squared over 2 or y squared. This is hy. We place the value of hy in the original solution. So we get 3x squared y plus 4x plus y squared, which is hy, is equal to c. That's the general solution. Again, if we have values for x and y, like an initial condition, you can get the value of c and you place it back within the general solution to get the particular solution. Another type of first order differential equations is Bernoulli's equation. A Bernoulli equation has the following form: dy over dx plus p of x y equal q of x y to the power of n. Now, if n equals 0 or n equal 1, it becomes linear. P of x and q of x are functions of x as usual. So this is a little bit complicated. How to solve? At first, we need to divide by y to the power of n, or in other words, multiply by y to the power of minus n, the entire equation. Okay, so you get y to the power minus n dy over dx plus p of x y to the power 1 minus n is equal to q of x. We substitute v with y to the power 1 minus n to get the following, which is dv over dx is equal to 1 minus n y to the power of n dy over dx. Then we solve y by replacing it in the first equation. Of course, we use the method of integrating factors to solve for v. Then we replace back v by y to the power 1 minus n. So we get a linear equation in v that we solve using the integration factor method. We retrieve the value of y by swapping y and v, y to the power of 1 minus n and v. That's the final step. Example: dy over dx plus y equal y squared, which has the form, of course, dy over dx plus p of x y equal q of x y to the power of n, where n in this case is equal to 2. So we multiply by y to the power minus n, which is y to the power minus 2. So y minus n times dy over dx plus y to the power of minus n times y is equal to y power minus n times y squared. So y to the power minus n times dy over dx plus y to the power 1 minus n equal y 2 minus n. We're still dealing with n here. We haven't replaced the real value. Let v is equal or be equal to y to the power of 1 minus n. Then according to the chain rule, the derivative of v over x is equal to derivative of v in respect of y times derivative of y in respect of x, which implies that derivative of v in respect of x is derivative of v in respect of y, which is 1 minus n times y to the power 1 minus n minus 1 times dy over dx, which gives us dv over dx is equal to 1 minus n times y to the power minus n dy over dx. Let's multiply by y to the power of minus n using the real value of n this time. So y minus 2 dy over dx plus y minus 2 times y, which is equal to y minus 1, equal y minus 2 times y2 or 1, because it gives us y to the power of 0. So y minus 2 dy over dx plus y to the power of minus 1 is equal to 1. Then let v be equal to y to the power of 1 minus n, which is equal to y to the power of minus 1. dv over dx becomes the derivative of this quantity, which is 1 minus n times y to the power of minus n dy over dx, so equal to minus 1 y to the power of minus 2, because y minus 1, which is y to the power minus 2, times dy over dx. That's dv over dx. And these are the different arguments. So v equal y to the power of minus 1, and dv over dx is equal to minus 1 times y to the power of minus 2 dy over dx. Let's replace them in the equation above, which is this one. So you get minus dv over dx plus v, which is y to the power of minus 1, is equal to 1. And we need to solve it using the integration factor method. So dv over dx minus v is equal to minus 1. We need to change the sign to the other side. P of x is equal to minus 1, and q of x is equal to minus 1. We have, you can say, linearized this equation, okay, in order to solve v. So mu of x is equal to e to the power of integral p of x dx, which is equal to e minus x, multiply by mu of x, the entire equation. So you get e minus x dv over dx minus e minus x, which is plus v. It became minus v here. That's the equation we are working with. So minus e minus xv equal minus e minus x, which gives us derivative of e minus xv, that's the form, over the x is equal to minus e minus x. And you multiply by the x, the other side of the equation, or the equality. So integral d e minus xv is equal to minus integral e minus x dx. Then v e minus x is equal to minus x, or e minus x, but you have minus and minus, it becomes plus c, which is the constant of integration for v. Remember, we need to retrieve back the value of y. So v is equal to 1 plus c e x. Continuing on, so we get v. We need to replace back v with its value, which is v equal y to the power of minus 1. Okay, so y to the power of minus 1 equal 1 plus cex. Then y is equal to 1 over 1 plus cex. That's the general solution. That's the final solution. Exercise. dy over dx plus 2 over xy is equal to x squared y to the power of 3, with x is greater than 0. Of course, you can try at it yourself. Why x greater than 0 is necessary? Because you have a division by x. That's why. Okay, so what we can identify immediately is p of x is the part multiplied by y, and q of x is that multiplied by y to the power of 3, with n equal 3. So p of x is equal to 2 divided by x, q of x is equal x squared, with n equal 3. Let v equal y to the power of 1 minus n, which is y to the power of minus 2. Then dv over dx is equal to minus 2 y to the power of minus 3 dy over dx. So minus 1 over 2 dv over dx is equal to 1 divided by y to the power of 3 dy over dx. We simply multiplied by minus 2 this denominator here, and y to the power of minus 3 is equal to 1 over y3. That's normal. Multiplying the entire equation by y to the power of minus 3, you get 1 divided by y3 dy over dx plus 2 divided by xy square, because you have 1y here. Okay, so by elimination you get 2 over x times y to the power of 2 equal x square, because y minus 3 times y to the power of 3 is equal to 1, which is y to the power of 0. Placing v in the equation, so you replace dy over dx with minus 1 over 2 dv over dx, which is this quantity here, plus 2 over x times v, because plus 2 divided by x times v, which is y to the power of minus 2, okay, which is this quantity here. Why? Because 1 over y2 is equal to y to the power of minus 2 equal x squared. Minus 1 half dv over dx plus 2 over xv equal x squared, which is equal to dv over dx minus 4 over xv equal minus 2x squared. We simply eliminated the 2 in the denominator here, which was multiplied by dv over dx, and the minus by multiplying by simply minus 2, the entire equation. This is how you get rid of minus 2 in the denominator. Okay. Then we solve it according to linear equations. So we need to get the integration factor. U of x is equal to e integral p of x dx is equal to integral, or e minus integral 4 over x dx, which is equal to e minus 4 ln x, or e ln x to the power of minus 4, which is 1 divided by x4. We multiply 1 by mu x, okay, which is this equation. So you multiply it all together by 1 divided by x4. You get 1 over x4 dv over dx minus 4 over x5v equal minus 2 over x squared. So the derivative of 1 over x4v over dx is equal to minus 2 over x squared. Remember, we are solving it according to linear equations, okay? Which means d of 1 over x4v is equal to minus 2x to the power of minus 2. We moved x2 to the numerator times dx. After that, we integrate both sides. Alright, let's integrate. So integral of d, the derivative of 1x4 times v, is equal to minus integral, because the minus you can move it outside of the integral, 2x to the power of minus 2 times dx plus c. Alright, integral of a derivative simply gives you what's within the derivative, which is v divided by x4 is equal to divided by x. That's the integral value of x to the power of minus 2, and you have 2 on the outside, okay? So plus c. It simply gets you x to the power of minus 2 plus 1, which is x to the power of minus 1 divided by minus 1. That's why you have 2 over x plus c. So v is equal to x3 plus c x4. Then we get the value of y in respect of v, or from v. Swapping v with y to the power of minus 2, so 1 over y squared is equal to 2x3 plus c x4. Then y squared is equal to 1 divided by 2x3 plus c x4. So y is equal to 1 over the square root of 2x3 plus cx4. Of course, if we have initial conditions, you can easily find c and place it back in the equation, the general solution rather, to get a particular solution. Another one with a little bit of a different style. dy over dx minus y equal y squared sine x. The form is dy over dx plus p of x y equal q of x times y to the power of n. P of x is equal to minus 1 as you notice. Q of x is equal to sine x and n equal 2. So at first we multiply by y to the power of minus 2 or minus n. So y minus 2 dy over dx minus y to the power of minus 1, because y minus 2 times y is y minus 1 equals sine x. Then we need to replace it by v. So let v be equal to y to the power of 1 minus n, which is y minus 1. Then dv over dx is equal to minus y to the power minus 2 dy over dx, which gives us minus dv over dx here, and then you have a v or minus v over here, okay, equal sine x. So let's check it out. Minus dv over dx minus v equals sine x, or dv over dx plus v is equal to minus sine x. Now, at first, we need to get the integration factor. Remember, we've linearized the equation by using the v instead of y, by swapping these two values. So, mu of x is equal to e integral of p of x, which is e integral of dx simply, or equal to ex. Then, multiply by mu x the entire equation, so ex dv over dx plus vex is equal to minus sine x ex. So dex v over dx is equal to minus sine x ex. You multiply the x by the second component of the equation, which is the part to the right. So exv, because integral of the derivative is exv, equal minus integral sine x ex dx plus c. exv is equal to minus integral sine x ex dx plus c. In order to solve it, we need to go to the change of variables. So let u be equal to ex, du then is equal to ex dx, dv equal to sine x, then v is equal to minus cosine x. So integral of u dv is equal to uv, u times v, minus integral of v du, which is minus cosine x times ex dx. So integral sine x ex dx is equal to minus ex cosine x minus integral of minus cosine x ex dx. You go to, okay, integral sine x ex dx equal minus ex cosine x plus integral of cosine x ex. After that, we need to also again use the same method, okay, to solve integral cosine x ex dx. So u equal ex, du equal ex dx, dv equal cosine x, v equal sine x. So integral sine x ex dx is equal to minus ex cosine x plus ex sine x minus integral sine x ex dx. You see this one here, we can move it to the left. So you get 2 integral sine x ex dx equal to the following. So 2 integral sine x ex dx is equal to minus ex cosine x plus ex sine x. Then integral of sine x ex dx is equal to 1/2 ex times sine x minus cosine x. Integral sine x ex dx is equal 1/2 ex times sine x minus cosine x. We need to replace it down below in the original equation, which is exv equal minus integral sine x ex dx plus c. So exv is equal to minus 1/2 ex sine x minus cosine x plus c. V is equal then to minus 1/2 sine x plus 1/2 cosine x plus c over ex. Again, you need to remember to swap back v with its value in respect of y. So v equal y minus 1 because we need to find y. 1 over y is equal to 1/2 cosine x minus 1/2 sine x plus c over ex. 1 over y is equal, can be written in a different way, ex times cosine x minus sine x plus 2c divided by 2ex. We simply took a common denominator, which is 2 times ex. then y becomes 2 times ex, or 2ex, divided by ex times cosine x minus sine x plus 2c. That's the general solution. Second and higher order linear ODEs, the general theory. The general theory of linear ODEs applies for first order and higher order linear differential equations. It provides a systematic approach to solve these equations involving derivatives of unknown functions. A linear ODE has the following generalized form, which is an x times dn y over dxn, which is the nth derivative of y, plus a n minus 1 dn minus 1 over dx n minus 1 y, the n or nth minus 1 derivation of y, etc., all the way to a0x y is equal to fx. Now, y is equal to yx is the unknown function, aix are known coefficients. If fx is equal to 0, the equation is called homogeneous. Otherwise, it is not homogeneous, or it is non-homogeneous. Superposition principle. For a homogeneous linear ODE, if y1 of x and y2 of x are solutions, then c1 y1 of x plus c2 y2 of x is also a solution. This is the principle of superposition. General solution structure. So for the homogeneous case, L of y is equal to 0 because the second part is 0. The general solution would be c1 y1x plus c2 y2x plus etc. plus cn ynx, where y1 up to yn is a set of solutions. For non-homogeneous case, L of y is equal to fx, so the second counterpart of the equation is not 0. The general solution would be y of x is equal to yh of x, which is the homogeneous solution, supposing that fx was equal to 0. That would be the solution. This is what it means. Plus yp of x, which is the particular solution for the non-homogeneous equation, for f of x being present. This is what we're talking about. So again, y of x is equal to yh of x plus yp of x, where yh is the general solution for the homogeneous part of the equation, given that fx is supposed to be 0, and yp is the particular solution for the non-homogeneous equation being there, okay, being present. Second and higher order linear ODEs, homogeneous equations with constant coefficients. The generalized form of a differential equation of a higher order is anx dny over dxn plus an minus 1 dn minus 1 y over dxn minus 1, etc. Again, where n and n minus 1, all these coefficients are the nth derivatives, like here the nth derivative or the nth minus 1 derivative for y. Okay, so the solution involves solving the characteristic polynomial of the form an r to the power of n plus an minus 1 r to the power of n minus 1, etc. all the way to a0. We find the roots for this equation, r1, r2, all the way. The nature of these roots will reveal the form of the general solution. So if we are dealing with distinct roots, y of x is equal to c1 e r1x plus c2 e r2x plus c3 e3 e r3x all the way, okay, where r1, r2, r3, and rn are the distinct roots, which means they are different roots. Repeated real roots, r is the root of multiplicity, meaning that it is a double or triple root. So erx, the solution would be erx plus xerx plus x squared erx, okay, depending on the number of the multiple roots. Finally, complex roots, if r equal to alpha plus minus beta e, where there was no solution in the real or among the real numbers, then the solution would be y of x is equal to e alpha x cosine beta x plus e alpha x times sine beta x, where alpha and beta are respectively the real and the imaginary part of r, which is the root. Example. Let's say we have the equation, differential equation of second order, because the highest derivative is y second minus 5y prime plus 6y is equal to 0. So how to solve it? We need to at first turn it into the polynomial form. So the polynomial equation is r squared minus 5r plus 6 is equal to 0. So we need to find the roots for this equation, or where this equation becomes 0. This is the equation of the form ar squared plus br plus c is equal to 0. We need to find the discriminant, which is delta. So how do we find delta? At first, let's review on how to solve a second degree polynomial equation. So finding the discriminant, delta is equal to b squared minus 4ac. This is the discriminant. Finding the roots based on delta, here we have three cases. At first, if delta is greater than 0, you have two distinct roots. r1 is equal to minus b minus square root of delta divided by 2a, and r2 is equal to minus b plus square root of delta divided by 2a. If delta is equal to 0, then square root of delta is equal to 0. Hence, r1 is equal to r2 is equal to minus b divided by 2a. So you have a double root or a multiple root, r1 equal r2 equal minus b divided by 2a. Then, third case, if delta is less than 0, we solve it as a complex number by replacing the minus sign by I squared. So delta is equal to, instead of minus 4, this becomes 4i squared. Hence, r1 and r2 would be equal to minus b minus square root of delta, which is now 4i squared, divided by 2a, and r2 minus b plus square root of delta divided by 2a. Going back to our differential equation, of course you can pause the video and try to solve it yourself. So we first transform it into a second degree polynomial equation, which is r squared minus 5r plus 6 is equal to 0, or which is the form a r squared plus br plus c, where a equal 1, b equal minus 5, and c equal 6. The discriminant delta is equal to b squared minus 4ac, which is 25 minus 4 times a times 6, which is 24, equal 1. So delta is equal to 1. Let's find the different roots. r1 is equal to minus b minus square root of delta over 2a, which is 5 minus 1 over 2, or 2. r2 equal minus b plus square root of delta divided by 2a, which is 5 plus 1 divided by 2. 6 divided by 2 is 3. These are two distinct roots. Then the general equation or solution is y of x is equal to c1 e to the power of the first root times x, which is 2x, plus c2 e to the power of the second root 3 times x. Second example, repeated roots scenario. You have y second minus 4y prime plus 4y is equal to 0. At first, as usual, we need to flip it into the polynomial form, which is r squared minus 4r plus 4 equals 0, or the general form is ar squared plus br plus c is equal to 0. A equal 1, b equal minus 4, and c equal plus 4. Let's find the discriminant. So delta is equal to b squared minus 4ac, which is 16 minus 4 times 4, also 16, equals 0. So delta is equal to 0. Then we have a double root or multiple root. So r1 is equal to r2 equal minus b divided by 2a, which is 2. r1 equal r2 equal 2. Then the general solution is y of x is equal to c1 e to x plus c2 x e to x. Okay? Or you can simplify it by y of x is equal to c1 plus c2x times e to x. You see the common denominator, or the common factor rather, is e to x multiplied by c1 plus c2x if you have 4 roots, you get c3x squared, then c4x to the power of 3, etc. Third example, complex roots scenario. Okay, so you have y squared or y second degree, or second order rather. It becomes second degree in the polynomial form, plus 4y is equal to 0. Okay, now here, when you flip it to the polynomial form, you get r squared plus 4 is equal to 0. Then r squared equal minus 4. You don't need, in this case, to solve for delta. Okay, it can be simply found, the roots can be simply found by moving 4 to the right. So r squared is equal to minus 4. It is unsolvable in R. Why? Because the square cannot be negative. Then we need to find it, or find the solution in the complex numbers, among the complex numbers. So you simply change minus 4 into 4i squared. So r becomes equal to plus minus 2i. You have 2 roots. Okay, one is plus 2i, the other is minus 2i. Why? Because r is squared. So alpha is equal to 0 because the real part of this complex number is 0, and the imaginary part, which is beta, is equal to. The solution becomes, which is the general solution, you have r equal alpha plus minus beta e. So e alpha x times cosine beta x, with alpha is 0, and e alpha x sine beta x. Hence the general solution becomes c1 e alpha x cosine beta x plus c2 e alpha x sine beta x, or c1 cosine 2x plus c2 sine x. Exercise. We have y to the second order derivative minus 3y prime first order derivative plus 2y is equal 0, with initial conditions y of 0 equal 4, y prime of 0 equal 5. Of course, you can pause the video, try to solve it yourself, and get back to the solution. At first, let's change it into its polynomial form. R squared minus 3r plus 2 equal 0, which is the form ar squared plus br plus 0. Then we need to find the discriminant, which is delta. So delta is equal to b squared minus 4ac, which is 9 minus 8 equal 1. So delta is equal 1. Then we have, since delta is greater than 0, we have 2 distinct roots. The first root is r1 is equal to minus b minus square root of delta divided by 2a. So 3 minus 1 divided by 2 equal 1. That's the first root, r1 equal 1. r2 equal minus b plus square root of delta divided by 2a equal 3 plus 1 divided by 2, which is 4 divided by 2, or 2. Then r2 equal 2. So since delta is greater than 0, we have 2 distinct roots, and the general solution is y of x is equal to c1 ex plus c2 e2x. Based on the initial conditions, we need to find c1 and c2. So y of 0 is equal to 4. But at first we need to find y prime, which is the first derivative of the solution. So y prime of x is equal to c1 ex plus 2 c2 e2x. Okay, y of 0 equal 4. We replace x and y in the first solution, which is the general solution. So you have c1 plus c2 is equal to 4. Then y prime of 0 equal 5. So c1 plus 2c2 is equal to 5 in the derivative this time. And in order to solve it, you simply multiply by minus the first equation. So you get 2c2 minus c2 equal 5 minus 4, and c1 cancels out. So c2 should be 1. So based on the general solution and based on the initial conditions, we can find the particular solution. Going back to solving the system of equations that we've gotten through the initial conditions on y and y prime, the function and the first derivative, you get minus c1 minus c2 equal minus 4. We multiplied the first equation by minus. Then you add up the two equations. So you get 1 plus 2 would give you, or 2 plus 1, which is the same thing, C1 minus C1 plus 2C2 minus C2 equal 5 minus 4, then C2 equal 1. Then you place it back in one of the equations to get C1. So C1 plus C2 equal 4, then C1 equal 3. So we've gotten C1 and C2. To find the particular equation, we simply place them back in the general solution. Hence, the particular solution is equal to y of x is equal to C1ex, which is 3ex, plus C2ex, which is 1e2x. Okay, so 3ex plus e2x is a particular solution for the differential equation. Another one, y to the second order plus 6y prime plus 9y equals 0, with initial conditions y of 0 equal 2 and y prime of 0 equal minus 3. So try to solve it. You can pause the video and get back to the solution later. Okay. The polynomial form is r squared plus 6r plus 9 equals 0, or ar squared plus br plus c equals 0, where a equal 1, b equals 6, and c equal 9. Let's find the discriminant, or delta. So delta is equal to b squared minus 4ac, which is 36 minus 4 times 9 times 1. 36 minus 36 equal 0. So we have a double root or a multiple root. The multiple root is r1 equal r2 equal minus b over 2a, which is minus 6 over 2, or minus 3. Hence, the general solution becomes, and by the way, this is the formula, if you want like a formula for the multiple root, y of x equal sigma I equals 0 to n minus 1, c I plus 1, because the first constant is c1, times x to the power of I, so the first one is x to the power of 0, e times rx, okay? And then you keep going, you keep elevating the power of x as you go along, with m is equal to n minus 1 and n, or which is the number of roots. So m equal n minus 1 is the number of roots. Okay, so the general solution is equal to c1 e minus 3x plus c2x e minus 3x, with r1 equal r2 equal minus 3, that's the multiple root. So y prime x is equal to minus 3 c1 e minus 3x plus c2 times e minus 3x minus 3x e minus 3x, okay? We are finding y prime in order to solve the particular solution, or to find the particular solution. So this is the general solution for y of x, and that's the derivative in order to find y prime of 0 equal minus 3. To get from it c1 and c2, we need to use both equations. So we've gotten the general solution and the first order derivative, y prime of x, which is necessary because one of the initial conditions depend on it. And as a side note here, the derivative of y of x, the second part, which is derivative of c2x e minus 3x, c2 of course is a constant, it doesn't matter, but this is a product. So derivative of a product is equal to, let's say, u equal x and v equal e minus 3x, then it is u prime v, which is 1 times e minus 3x, plus u v prime, or x times derivative of e minus 3x, or minus 3x e minus 3x. Okay? So we need to plug in the initial conditions in y of x and y prime of x respectively. You get, okay, y of 0 is equal to 2, then 2 equal c1, because c2 cancels out since x is equal to 0, and you plug y prime of 0 equal minus 3, so minus 3 is equal to minus 3 c1 plus c2, okay? Because here x is equal to 0 and e to the power of 0 is equal to 1. So c1 equal 2, you place it back in the second equation to find c2. Hence, minus 3 c1 plus c2 is equal to minus 3. So minus 3 times 2 plus c2 is equal to minus 3, then c2 is equal to 3. We've gotten c1 and c2 you can place them back in the general solution to get the particular solution. So the particular solution is equal to y of x equal c1 e minus 3x, which is 2 times e minus 3x, that's c1, plus c2x e minus 3x, which is 3x e minus 3x. So, and you can factor it out. Y of x is equal to 2 plus 3x times e minus 3x. That's the particular solution. Another one, y second minus 2y prime plus 5y equals 0 with the following initial conditions: y of 0 equal 1, y prime of 0 equal 0. Also, you can pause the video. Okay, so let's start with it. Polynomial form is r squared minus 2r plus 5 equals 0, or ar squared plus br plus c equals 0. Let's find the discriminant delta. Delta is equal to b squared minus 4ac is equal to 4 minus 4 times 5. So 4 minus 20, which is minus 16. Notice that delta is less than 0. So we don't have any roots within the real numbers. We need to move or transition into the complex numbers. Okay? We do that by considering minus 1 is equal to I squared. So delta is less than 0. Solution is within the complex numbers, not in the real numbers. I squared is equal to minus 1. Delta is equal to 16 I squared. This is how we cancel out, or we swap the minus sign with I squared. Let's find the roots in this case. So R1 is equal to minus b minus square root of delta divided by 2a, which is minus b, so minus 2, which is 2, minus 4i, the square root of 16i squared divided by 2 equal 1 minus 2i. So R1 is equal to 1 minus 2i. R2 equal minus b plus square root of delta divided by 2a, which is 2 plus 4i divided by 2, or 1 plus 2i. So R2 is equal to 1 plus 2i, which is the form R equal alpha plus minus beta e. So alpha is 1 and beta equal 2. We need to place them within the solution. Y is equal to C1 e alpha x cosine beta x plus C2 e alpha x sine beta x, with alpha equal 1 and beta is equal 2. So y of x is equal to C1 ex cosine 2x plus C2 ex sine 2x. Let's continue. So we've gotten the general solution. We need the particular solution. At first, let's find y prime of x. So we need to derive y in respect of x. So y prime of x is equal to c1 ex cosine 2x minus 2 ex sine 2x. Okay, that would be u prime v plus u v prime, remember, plus c2 ex sine 2x plus 2 ex cosine 2x. Then we place y0 equal 1 and y prime 0 equals 0, which are the initial conditions. So this gets you, for y0 equal 1, 1 equal c1, because you have sine 0 is equal to 0, cosine 0 1, and e0 1. For the second equation, or the second condition, y prime 0 equals 0, so you have 0 equal cosine 0 is 1, and plus you have, okay, I'm sorry, this is in the second equation, so you have c1, which is here, cosine 0, and ex for x equals 0, that's 1. This cancels out, plus c2 times 2, because you have the derivative of 2 ex cosine 2x. So this term is 1. You have 2 c2, and the first term is 0. Hence, you place c1 equal 1 in the second equation. So you get 2 c2 equal minus 1. Then c2 equal minus 1 divided by 2. Okay. So the particular solution becomes y of x is equal to c1 ex cosine 2x, with c1 is 1, okay, minus c2 is minus 1/2, so minus 1 over 2, ex sine 2x. Fast review: the general form of a linear ODE is then the following: an dny over dxn plus an minus 1 dn minus 1 over dxn minus 1. These are all n order derivatives or n minus 1 order derivative, etc. Okay, now you can formalize this equation into sigma from I equal n to 0 ai d I y over dxi. Okay, so this can be rewritten this way if you want to memorize it. Now we convert it to a polynomial form. So an rn plus an minus 1 rn minus 1 plus a1 r plus a0 equals 0, which can be rewritten sigma I equal 1 to 0 ai r to the power of I. Second order polynomial solution. Okay, so here I hope this is clear. So I equal n all the way down. This is a countdown to 0. ai ri, which is an rn plus an minus 1 rn minus 1 all the way down to a0. Second order polynomial form solution. When we have distinct roots, delta greater than 0, then the distinct roots are y of x is equal to sigma I equals 0 to n c I plus 1 e or exponential of ri x. Okay, so r1, r2, r etc. Okay, times x. Then if delta is equal to 0, we have multiple roots, and this is how we can write it. Y of x is equal to sigma I equals 0 to n c I plus 1 times x to the power of I. So for the first element, you have x0, which is 1. E ri times x plus x erx plus x2 erx, etc. Okay, depending on the number of roots. So second order polynomial form solution, again, for delta greater than 0, distinct roots, y of x is equal to sigma I equals 0 to n c I plus 1 eri x. For delta equals 0, then multiple roots, y of x is equal to sigma I equals 0 to n c I plus 1 xi to the power of I eri x. Then for delta less than 0, we have complex roots which have the form y of x is equal to c1 e alpha x cosine beta x plus c2 e alpha x sine beta x. Non-homogeneous differential equations. The non-homogeneous differential equation has the following form, the same form as the homogeneous actually, which is anx dny over dxn plus an minus 1 x dn minus 1 y over dxn minus 1 all the way to a0 xy, but instead of being equal to 0, it is equal to gx, where gx is a function different than 0. The general solution of a non-homogeneous ODE is the following. Y of x is equal to yh of x plus yp of x, where yh of x is the general solution for the homogeneous part. Like when we consider or regard g of x as being 0, okay, we like claim it as 0 at first to find the general solution, then yp of x, which is the particular solution for the non-homogeneous part of the equation. How to solve? First, we set g of x is equal to 0 and we solve the equation as homogeneous to find the general solution yh of x. Then to find the particular solution yp of x, we use one of the following methods. Method of undetermined coefficients for simpler g of x, and second, variation of parameters, which is more general when coefficients are constant and g of x is integrable. So for the method of undetermined coefficients, we need trial solutions. Let's say g of x is of the form e alpha x, then the trial solution is a e alpha x. If it is sine beta x, cosine beta x, trial solution is a cosine beta x plus b sine beta x. If it is x to the power of n, trial solution is axn, bxn minus 1, etc. And if it's a combination, let's say x squared ex, then the trial solution is ax squared plus bx plus c times ex. Let's say we have g of x is equal ex, and based on the suggested trial, we ought to have yp of x is equal to aex. Then we get y prime p of x and y second p of x, and we place them in the ODE to find a. Finally, the final solution is y of x is equal y h of x, which is the general solution for the homogeneous equation, plus yp of x, where again y h of x is the general solution for the homogeneous part again, and yp of x is the particular one. Example, y second minus 3y prime plus 2y equal ex. At first, we need to solve the homogeneous part of the equation while considering g of x is equal to 0, which is the second part of this equation. The polynomial form of the homogeneous part, g of x is equal to 0, is r squared minus 3r plus 2 is equal to 0. So let's find the discriminant. Delta is equal to b squared minus 4ac, which is 9 minus 4 times 1 times 2, 9 minus 8 equal to 1. Greater than 0, so we have two distinct roots. R1, first root is minus b, 3 minus square root of delta divided by 2, so 2 divided by 2 equal 1. Second root is equal to minus b plus square root of delta, 3 plus 1 divided by 2 equal 2. So the general solution for the homogeneous part is y h of x is equal to c1 ex plus c2 e2x, with 1 and 2 are the two different roots. Finding the particular solution, if we use yp of x is equal to aex, it cancels out since yp equal y prime p equal y second p, and the ODE becomes aex minus 3aex plus 2aex, which is 0. So let's write the form yp of x is equal to ax ex instead. So yh of x is equal to c1 ex plus c2 e2x. Finding the particular solution, we consider yp of x is equal to ax ex. So let's find the different derivatives for yp. You have y prime p of x is equal to aex plus ax ex. So we factor out a, it becomes a times ex plus xex. And y second p is equal to aex plus ax ex. We simply got the derivative of this term. Okay, we place them back into the equation. Then a times 2ex plus xex minus 3 y prime, which is aex plus xex plus 2axex equal ex. So which is equal to 2aex plus axex. You see here you have axex and 2axex. They cancel out with minus 3axex. So we are left with 2aex minus 3aex equal ex, which is minus aex equal ex. So a equal minus 1. Again, yx is equal to yhx plus ypx, the homogeneous solution plus the particular solution. So yx is equal to c1 ex plus c2 ex plus the particular solution, which is of the form ax ex. A is equal to minus 1, so y of x is equal to c1 ex plus c2 e2x plus ax ex, which is yp, and a minus 1, so minus x ex. Exercise y second plus y equal cosine x. So you can pause the video and try to solve it. Now let's move on. At first we need the homogeneous solution, which is considering the second part, or cosine x equal 0. So homogeneous solution is given by the polynomial form r squared plus 1 equals 0, then r squared equal minus 1. No solutions in r, in real numbers. So we consider minus 1 equal to I squared, then r equal plus minus I. Okay, so alpha is equal to 0 and beta is equal to 1 because the number or the root is of the form alpha plus beta I. Okay, so beta equal 1, alpha is 0. There's no real part. And the solution is yx equal yh of x, which is the general homogeneous solution, plus ypx, which is the particular solution. So yh of x is equal to c1 cosine x with beta equal 1 plus c2 sine x. Remember, alpha is equal to 0. Now let's find the particular solution. So the particular solution have the form of ypx is equal to ax cosine x plus bx sine x. We need to find a and b for that matter. Y prime p x, because we need y second here. So let's derive y prime p x is equal to a times u prime v plus uv prime, which is cosine x, minus x sine x, because derivative of cosine x is minus sine x, plus b sine x, which is u prime v, plus x cosine x, the derivative of sine x. Okay, then y second is equal to a times minus sine x plus x cosine x, that's all derivative, plus b cosine x plus cosine x minus x sine x. We place y second and y in the first equation equal to cosine x. So all of that is equal to cosine x, which is y second plus y bx. Then, okay, you eliminate bx sine x, because you have minus bx sine x plus bx sine x. They cancel out. Then minus ax cosine x plus ax cosine x. They cancel out. So we are left with minus 2a sine x plus 2b cosine x is equal to cosine x. We pair together these similar components. So minus 2a sine x is equal to 0, because we don't have a sine x to the right. Then a is equal to 0 divided by minus 2 equal 0. Then 2b cosine x is equal to cosine x, so b equal 1/2. So a equals 0, b equal 1 over 2. Let's continue. So we've gotten the homogeneous equation, and now we have a and b for the particular solution. So yp of x is equal to ax cosine x plus bx sine x, which is equal to 1/2 x sine x, because b equal 1 divided by 2 and a is equal to 0. You simply add up yp of x to yh of x to get the full solution. So y of x is equal to yh of x plus yp of x equal c1 cosine x plus c2 sine x plus 1 divided by 2 x sine x. This is the particular solution, and this is the generalized solution of the homogeneous ODE. This is finally y of x. Another exercise, y second plus 4y equals sine 2x. You can pause the video and try it yourself as usual. Okay, so the homogeneous solution is you have r squared plus 4 equals 0, then r4 is equal to minus 4. Okay, no solutions in the real numbers, so we consider minus 1 is equal to I squared, r squared is equal to 4i squared, then r equal plus minus 2i, with alpha equal 0 and beta equal 2. So the general solution is yh of x is equal to c1 cosine 2x plus c2 sine 2x. Remember, alpha is 0 and beta equal 2, which is the imaginary part of the roots. Okay. Particular solution, yp of x is of the form ax cosine 2x plus bx sine 2x. So let's solve the different derivatives to get to y second, and we fill in the first equation. So y prime p is equal to a cosine 2x u prime v plus uv prime minus 2x sine 2x, because the derivative of cosine 2x is minus 2 sine 2x, plus b sine 2x plus 2x cosine x. Derivative of sine 2x is 2 cosine 2x. Y second of p is equal to, again we continue, a times minus 2 sine 2x minus 2 sine 2x minus 4x cosine 2x plus b 2 cosine 2x plus 2 cosine 2x minus 4x sine 2x. Placing back the values of yp, y prime p, which is not available here, and y second p in the original ODE. So you get this entire equation. So, okay, we expand a minus 2 sine 2x minus 2 sine 2x minus 4x cosine x, etc. equal to sine 2x. Now we need to cancel out the equivalent components that are plus and minus, either positive or negative. Okay, so minus 4bx sine 2x cancels out with plus 4bx sine 2x on one hand. On the other hand, we have minus 4ax cosine 2x plus 4ax cosine 2x also cancel out. So we are left with minus 4a sine 2x plus 4b cosine 2x equal sine 2x. Then we have a system of equations. 4b cosine 2x is equal to 0, and minus 4a sine 2x is equal to sine 2x. So b is equal to 0 and a equal minus 1 divided by 4. These are a and b for the particular solution. So we place a and b in the particular solution, and you get, of course, b is equal to 0, then yp of x is equal to minus 1 4 x cosine 2x. You have yp of x and yh of x. Hence, the full solution, y of x is equal to yh of x plus yp of x equals c1 cosine 2x plus c2 sine 2x minus 1 4 x cosine 2x. Now we will go into another method of solving differential equations, which is the variation of parameters. So let's say we have y second plus y is equal to cosine x. At first, we need the homogeneous solution as usual. So you have the form of r squared plus 1 is equal to 0, then r squared equal minus 1. No solutions in r, so we consider minus 1 is equal to I squared. Hence, r squared is equal to I squared, r equal plus minus I, with beta is equal to 1. Okay, y of x is equal to yh of x plus yp of x. This is the full solution. Of course, alpha is equal to 0, which is the real part of the root, and beta is equal to 1. So, yh of x is equal to c1 cosine x plus c2 sine x. Then, in order to get the particular solution, you place yp of x is equal to u1 x cosine x plus u2 x sine x. u1 and u2 are to be determined. These are the unknown variables. Then you get this system of equations. So, u prime cosine x plus u2 prime sine x is equal to 0. That's the first equation. Then, minus u prime sine x, which is the derivative of the second counterpart, plus u2 prime cosine x is equal to cosine x. And we solve. You have this system of equation. How to solve it? We can convert it into a matrix. I usually use Cramer's method. You can use other methods that are also valid. So I place cosine x minus sine x cosine x in the first matrix. u1 prime, u2 prime are the unknown and equal to 0 cosine x. Now, after that, place 0 and cosine x within the second or the first matrix. Again, we are using Cramer's method. How do we use Cramer's method? This is how. You have 0 cosine x, you move them to the first column to solve for u1 prime, and before that even, we get the determinant of this matrix, which is cosine x times cosine x, minus times minus becomes plus sine x times sine x, which is cosine square x plus sine square x is equal to 1. This is delta. After that, you get delta u1 prime, which is placing 0 and cosine x in the first column here, instead of cosine x minus sine x. You place them back here, and you solve the determinant of delta u1 prime, which is minus sine x cosine x. And by the way, this is how we moved this other part from the right to the left. So delta u1 prime is given by the determinant of this matrix while replacing the first column with 0 cosine x. We have delta and delta u1 prime. So u1 prime is given by delta u1 prime divided by delta, which is minus sine x, cosine x divided by delta, which is 1. This is u1 prime. Okay? Now, delta u2 prime is given by 0 and cosine x. You place them in the second column. In the second column to solve u2 prime, because u2 prime is the second side, okay, the second argument. So you get cosine x minus sine x, and instead of sine x cosine x, you replace them by 0 cosine x. So, which gives us cosine square x. And here's the mechanism. 0 and cosine x are moved to the right column, which is sine x, cosine x, to replace these elements here. And we get delta u2 prime, which is equal to cosine square x. Hence, u2 prime is equal to delta u2 prime divided by delta equal cosine square x. Now we have u1 prime and u2 prime. We need to get u1 and u2 instead. So we need to integrate in respect of dx. So again, to find u1x and u2x, we need to integrate in respect of x. Let's start with u1 prime. At first, for u1 prime, you have minus sine x cosine x. Now, going back to the trigonometry identities, you have sine a plus b is equal to sine a cosine b plus cosine a sine b. Sine a minus b is equal to sine a cosine b minus cosine a sine b. For the sine, it respects the sign, okay, plus and minus, you can memorize it like this. And moreover, it goes with the other part, the other partner. So sine with cosine and cosine with sine. This is how you memorize it. As for cosine, it doesn't respect the sign. So if it's negative, it becomes positive. If it's positive, it becomes negative for the cosine a plus b, for example. And it goes with its partner. So cosine a plus b becomes cosine a cosine b minus sine a sine b. Cosines together and sines together. Okay, so this becomes, we add up 1 and 2 and let a equal b, because we have x and x here. So 2 sine a cosine a is equal to sine 2a, then sine a cosine a is equal to 1/2 sine 2a, which is the case here. You have sine x cosine x multiplied by minus. So u1 is equal to minus integral sine x cosine x dx is equal to minus 1/2 integral sine 2x dx, which is equal to plus 1/4 cosine 2x. This is u1. Let's find u2x, also integrating in respect of x. So for u2x, you have, for u2 prime rather, you have cosine square x. Okay, we go to the cosines. So cosine a plus b is equal to cosine a cosine b minus sine a sine b. As we mentioned before, the cosine does not respect the sign, so it flips the plus into minus. Okay, and cosine goes with cosine, sine with sine. Cosine a minus b is equal to cosine a cosine b plus sine a sine b. We have two equations, so add 1 and 2 and let a equal b. Then what we get, by adding both of the equations, you get 2 cosine squared a, which is this one because the sine has cancelled out, is equal to cosine 2a plus 1, which is cosine 0, by the way. Then cosine squared a is equal to 1/2 cosine 2a plus 1. We place back into the equation this value, so u2 is equal to integral of cosine squared x dx is equal to 1/2 cosine 2x plus 1. Then u2 is equal to 1 divided by 4 sine 2x plus x divided by 2. We've gotten the general solution y h of x is equal to c1 cosine x plus c2 sine x. Yp of x is of the form u1x cosine x plus u2x sine x. And we've solved u1 and u2. u1 is equal to 1/4 cosine 2x, u2 is equal 1/4 sine 2x plus x over 2. Then the full solution is equal to y h of x plus yp of x, which is y of x is equal to c1 cosine x plus c2 sine x plus 1/4 cosine 2x cosine x plus 1/4 sine 2x plus x divided by 2 sine x, which is u1 cosine x plus u2 sine x. That's a valid solution, although different than when using the other method, but it's a valid solution for this ODE equation. Another exercise, y second plus 4y equals sine 2x. So If you want, you can pause the video and try to solve it yourself. Okay, so r squared plus 4 is equal to 0. That's the polynomial form. R squared is equal to minus 4. R squared is equal to 4i squared because there are no solutions in R. Then R is equal to plus minus 2i or beta equal 2. Which gives us yh of x, the general solution of the homogeneous part, is equal to c1 cosine 2x plus c2 sine 2x, with 2 being beta, and alpha equals 0, which is the real part of the root. Then yp of x is equal to u1 cosine 2x plus u2 sine 2x, where u1 and u2 are unknown. They are needed to be found. So you form the equations u1 prime cosine 2x plus u2 prime sine 2x is equal to 0. Then you derive cosine and sine, so minus 2 u1 prime sine 2x plus 2 u2 prime cosine 2x, which is the derivative of sine 2x, is equal to sine 2x, which is the non-homogeneous part. Okay, so using Cramer's method to solve this system, of course you can use other methods such as Gauss, such as you have other methods, okay? I find this very convenient. So cosine 2x, sine 2x, then minus 2 sine 2x, and 2 cosine 2x form the first matrix, times u1 prime, u2 prime is equal to 0 sine 2x, which is this part. Moving on, so you have the matrices right now. We need at first to solve delta, which is the determinant of this matrix to the left. So delta is equal to the determinant of cosine 2x, sine 2x minus 2 sine 2x to cosine 2x, which is equal to 2 times cosine squared 2x plus, which is minus times minus 2 sine 2x times sine 2x plus 2 sine squared 2x is equal to, then delta equal to. Then delta u1 prime is equal to, you place 0 sine 2x to the left, okay, to the left part or the left column of the matrix. Then you get delta u1 prime 0 sine 2x, sine 2x to cosine 2x is equal to minus sine square 2x, which is 0 times this quantity becomes 0 minus sine square 2x. Then delta u1 prime is equal to minus sine square 2x. Hence, u1 prime is equal to delta u1 prime divided by delta is equal to minus 1/2 sine square 2x, which is minus sine square 2x divided by delta equal to. Okay, now let's solve for delta u2 prime. You place 0 sine 2x to the right of the matrix and you solve it. You solve the determinant rather. So delta u2 prime is equal to cosine 2x times sine 2x minus 0, which is cosine 2x sine 2x. Then u2 prime is equal to delta u2 prime divided by delta, which is 1/2 cosine 2x sine 2x. So u2 prime is equal 1 divided by 2 cosine 2x sine 2x. So we've gotten the two terms u1 prime and u2 prime. Now we need to get u1 and u2 by integrating. At first, for u1 prime, going back to the trigonometric identities, you know that cosine 4x, which is cosine a plus b when a equal 2x, is equal to cosine square 2x minus sine square 2x. And cosine 2x minus 2x, which is cosine 0 or 1, is equal to cosine square 2x plus sine square 2x. We need to multiply the first term by minus to cancel, this time the cosine square 2x, not the sine. And we add up both of the equations after that. So we multiply by minus, you get minus cosine 4x minus cosine square 2x plus sine square 2x. So cosine square 2x minus cosine 2x square cancel out. You have 1 and 2 equations, so we add them up and you get sine square 2x is equal to 1/2 times 1 minus cosine 4x, okay, because these terms cancel out. Here you have minus cosine 4x and here you have 2 sine square 2x. So sine square 2x is equal to 1/2 times 1 minus cosine 4x. So u1 is equal to minus 1/4 integral of 1 minus cosine 4x dx, because u1 prime is minus 1/2, and sine squared 2x is transformed into 1/2 times 1 minus cosine 4x. This is where the minus 1 divided by 4 comes from. Remember, this sine squared 2x is multiplied by minus 1/2 in u1 prime. So u1 is equal to minus 1 divided by 4 integral of 1 minus cosine 4x dx, which is minus 1/4 x minus 1 divided by 4 sine 4x. u2 prime equal 1/2 cosine 2x sine 2x. So we need to integrate u2. Now, in transformation, sine 4x is equal to 2 sine 2x cosine 2x. Then sine 2x cosine 2x is equal to 1/2 sine 4x. This is through the transformation by the trigonometric identities. You place it back in u2 prime, so you get 1 divided by 2 times 1 over 2 sine 4x, which is 1/4 integral of sine 4x equal to minus 1 divided by 16 cosine 4x. Hence, u2 is equal to minus 1 divided by 16 cosine 4x. So y of x, the final solution, is equal to h of x, which is c1 cosine 2x plus c2 sine 2x, plus u1, which is minus 1/4 x plus 1 over 16 sine 4x times cosine 2x, remember, minus 1 divided by 16 cosine 4x times sine 2x. This part is u2 and multiplied by sine 2x. These two together give us the particular solution, added to the homogeneous part give us the full solution. Another one, y second minus y is equal to ex. You can pause the video and try to solve it yourself. Okay, so the form or polynomial form is r squared minus 1 is equal to 0, then r is equal to plus minus 1. These are two distinct roots. Okay, so the solution, the general solution of the homogeneous part is given by y h of x is equal to c1 ex plus c2 e minus x. Let's find the particular solution using also the variation of parameters method. So yp of x is equal to u1 ex plus u2 e minus x. Let's find u1 and u2. So u1 prime ex plus u2 prime e minus x is equal to 0. That's the first equation. The second equation is u1 prime ex prime, which is ex also, plus u2 prime e minus x prime, which gives us minus e minus x times u2 prime is equal to ex. We add up the first and second equation, 1 plus 2, so you get 2 u1 prime ex is equal to ex, then u1 prime is equal 1 divided by 2. Minus 2 u2 prime e minus x, so you place back u1 prime in one of the equations to get u2 prime. So 2 u2 prime e minus x is equal to ex, then u2 prime is equal to minus 1 divided by 2 e2x. Now this one is easy. You should be able to solve u1 and u2 by integration straightforward. Alright, so let's find u1 and u2. u1 is equal to 1/2 integral dx equal x divided by 2. u2 is equal to integral of minus 1/2 e2x equal minus 1/4 e2x. So you got u1 and u2, you place them back in the particular solution. Hence, y of x, the full solution, is equal to c1 ex plus c2 e minus x plus x divided by 2, okay, plus x divided by 2 times ex, that's u1 ex, minus 1/4 e2x times e minus x, so it gives us minus 1/4 ex. Okay, of course you can factor them out and you get y of x is equal to ex placed to the side times c1 plus x divided by 2 minus 1/4 plus c2 e minus x. Systems of first order linear ODEs. Introduction to systems. A system of first order linear ODEs is a set of differential equations where each one is a linear in terms of its unknown functions and their first derivatives. The system of equations can be written like this: dx over dt is equal to a of t x of t plus f of t. X of t is a vector of unknown functions, x1, x2, etc. dx over dt is a vector of unknown derivatives. A of t is an n times n matrix, and f of t is a vector of known functions, or forcing vector also. The system is homogeneous if f of t is equal to 0 and non-homogeneous otherwise. If A is a constant matrix and f of t is equal to 0, then dx over dt is equal to A of t times x of t. The solution is through matrix exponentials where c is a constant and EAT times c is the matrix exponential of A. So x of t is equal to EAT times c. That's the form of x of t. If A can be diagonalized, which means A equal to P times D times P minus 1. D is the diagonal of the matrix, P is the left part below the diagonal, and P minus 1 is the right part, like after the diagonal, which is the inverse matrix of P. So EAT is equal to P exponential of dt times P to the power of minus 1. EDT is a diagonal matrix with E lambda I t, where lambda I or lambda i's are the eigenvalues of A. An eigenvalue is a scalar associated with a matrix that defines how much a matrix is squeezed or stretched. We're gonna get deeper into them after that, okay? We're gonna try practical examples, then you can understand it better. Having a system like the following, let's break it down into its constituting matrices. So dx1 over dt is equal to A11, which is A11. It means that this is the component or the coefficient of the first row, first column. A11 of t x1 plus A12 of t x2, which is the coefficient of the first row, second column. This is what it means, times x2 plus f1 of t. dx2 over dt is equal to A21 t x1, which is the coefficient of the second row, first column, plus A22, which is the coefficient of the second row, second column, x2 plus f2 of t. Unknown functions are x of t vector elements, which are x1 of t, x2 of t. So dx of t over dt, this can be rewritten in this form, is equal to a x of t plus f of t, where a is A11, A12, A21, A22 of t, and the non-homogeneous or forcing vector f of t is equal to f1 of t and f2 of t. Example on how to solve a system of ODE equations. dx over dt is equal to 3x plus 4y, dy over dt is equal to minus 4x plus 3y. So let's rewrite it. dx over dt is equal to a x of t, where dx over dt is the vector of derivatives, dx and dy over dt. A is the matrix to be determined, and x of t is equal to x of t, y of t, or vector of the unknowns. A is equal to 3, 4, minus 4, 3. After that, we need to compute the determinant of A minus lambda I equals 0, where I is the identity matrix having the same size of A matrix. Okay? With only the diagonals equal to 1. So A is equal to 3 minus lambda, 4, and minus 4, 3 minus lambda. Remember, we subtract by lambda only on the diagonal, okay? The diagonal elements is equal to 0. Let's determine the determinant. So 3 minus lambda square minus 4 times 4, which is plus 16, which gives you 9 minus 6 lambda plus lambda square plus 16 is equal to lambda square minus 6 lambda plus 25. Let's determine the roots of this equation. So delta is equal to b square minus 4ac, which is equal to minus 64 or 64i square. So we don't have solutions in the real numbers. We need to find them in the complex ensemble. Then lambda 1 is equal to minus b minus square root of delta. So this is b plus 6 minus square root of delta, which is 8i divided by 2, or 3 minus 4i. So lambda 1 is equal to 3 minus 4i. Lambda 2 is equal to 3 plus 4i. So we've gotten lambda 1 and lambda 2. Now we need to replace them back in the matrix. So for lambda 1 is equal to 3 minus 4i, you replace lambda in the A matrix, which is actually the determinant A minus lambda I rather. So 4i, 4 minus 4, 4i, xy, which gives you, when we take the first row, 4ix plus 4y is equal to 0. We choose an arbitrary value for x. Let's say for x is equal to 1, y equal minus I. So we've gotten the first vector v1. Then for lambda 2 is equal to 3 plus 4i, you get minus 4i, 4, minus 4, minus 4i, xy. Taking the first row, minus 4i x plus 4i, plus 4y rather, is equal to 0. For x is equal to 1, for y is equal to 4i, y equal I. So this is the second vector, 1i, or v2. And hence the solution becomes y of x is equal to c1 e 3 minus 4i times v1, which corresponds to the first root, plus c2 e 3 plus 4i times 1i, which is v2 that corresponds to the second root, lambda 2 is equal to 3 plus 4i. Exercise, dx over dt equal 2x plus 5y, dy over dt equal minus y. You can try to solve it and come back to the solution. So x of t, which is the set of variables or the vector for these variables, is equal to xy, a equal 2, 5, and 0 minus 1, because x is 0 in the second equation, and dx over dt is equal to a x of t. This is the form of the system. So determinant of a minus lambda I is equal to a equal 2 minus lambda, 5, and 0 minus 1 minus lambda. Remember, we subtract only the diagonal by lambda. Is equal to 0. Let's find lambda. So 2 minus lambda times minus 1 minus lambda is equal to 0. Then lambda 1 is equal to, and lambda 2 is equal to minus 1. It's so obvious here. You don't even need the discriminant. For lambda 1 is equal to, let's find the vector. So AV is equal to 0, 0, 5 minus 3. Okay, we place lambda in the matrix. We multiplied by v1 and v2. So 5 v2 is equal to 0, then v2 is equal to 0. And we choose an arbitrary value for v1. Let's say v1 is equal to 1. Then v1 is equal to 1, 0. Okay, for lambda 2 is equal to minus 1, we place lambda 2 within the matrix, so which is a minus lambda I, of course. You get 3, 5, 0, 0, v1, v2. Hence 3v1 plus 5v2 is equal to 0, or v1 is equal to minus 5 divided by 3 v2. Let's choose v2 is equal to 3, then v1 is equal to minus 5. So the vector v2 becomes minus 5, 3. We've chosen v2 equals 3 because it would be a convenient value to get rid of all fractions. So v2 is equal to minus 5 divided by, not divided, minus 5 and 3. We've gotten v1 and v2 from lambda 1 and lambda 2 respectively. The first vector corresponds to lambda 1 and the second to lambda 2. Let's place them within this equation. So you get x of t, y of t, actually the solution of this equation, which is x of t. So x of t, y of t is equal to c1 e lambda 1 x, which is 2x, times v1, which is 1, 0, plus c2 e minus x, or lambda 2x, times v2, or minus 5, 3. Another way to rewrite this equation is, or this solution, it is a set of solutions for x and y. Is x of t is equal to c1 e 2x minus 5 c2 e minus x, and y of t is equal to 3 c2 e minus x, which is the multiplication of c1 e 2x by this vector plus c2 e minus x by this vector. Okay, for each row you get x of t for the first one and y of t for the second one. Phase plane analysis. A phase plane shows the trajectory of the solutions of an ODE system in the 2D plane. At first, we need to find the equilibrium points, complying with AX equals 0, find eigenvalues and eigenvectors, as we've done already, characteristic polynomial, which is determinant of A minus lambda I equals 0. Also, we've done that so far. Solve for eigenvalues to get lambda 1, lambda 2, and find corresponding eigenvectors. What lambda tells us about the behavior of a function? If lambda is greater than 0, then the function is stretching. Remember, lambda is a scalar. It means that you are multiplying the matrix by a larger number, which is positive, so which makes the entire numbers blow up or blow out. So the function would be moving away from the origin. Why? Because you are stretching all the values. You are increasing the values of the matrix by increasing lambda. As an example, thermal expansion of the universe. Now, if lambda is less than 0, it means that you are multiplying by a negative value that is shrinking the function inwardly towards the origin. So it is like water spiraling down into a sink. That's the same analogy. Meanwhile, if lambda is equal to 0, it means that we have an equilibrium, so the function is neither expanding nor shrinking. It is in an equilibrium status. Okay, it's not increasing nor decreasing. Let's study different cases for the roots of lambda. Remember, you usually get more than one lambda, so one of them would be positive, the other would be negative, etc. You can have multiple scenarios. So if lambda I, the first root, is equal to 0 and lambda j is less than 0, it means that the solution or the solutions approach an equilibrium or a stable premise. They are shrinking to an equilibrium. If lambda I is equal to 0 and lambda j greater than 0, it means that the solutions are diverging along one direction because the other lambda is equal to 0. If both lambdas are equal to 0, then the entire phase plane is in a linear equilibrium. It's not changing. Non-diagonalizable with lambda equals 0, it means that the generalized eigenvectors lead to curved trajectories if you have a non-diagonalizable value. Okay, let's solve this example. Of course, you can pause the video and try to solve it yourself. Okay, so at first, let's rewrite this system as dx over dt, which is written d of x and y over dt, a, which is equal to 1, 1, and 0, 0. We have zeros in the second equation, and x of t is equal to x of t, y of t, x of t the vector. Okay, so you multiply 1 minus lambda times minus lambda, that's the determinant of a minus lambda I. It gives us 1 minus lambda times minus lambda is equal to 0. So lambda is equal to 0, which is lambda 1, and lambda 2 is equal to 1. For lambda 1 is equal to 0, you have, you place the value of 0 within this diagonal. So 1, 1, 0, 0, v1, v2 is equal to 0. Hence, v1 plus v2 is equal to 0. Let v1 is equal to 1, then v2 is equal to minus 1. That would be the first vector, or v1. Now, after that, so we've gotten v1 from lambda 1. We go to lambda 2. Lambda 2 is equal to 1. So 0, 1, 0 minus 1, v1, v2 is equal to 0. Remember, lambda, we place it in its corresponding placement within the diagonal. The value of lambda within lambda. So let v1, so you get, okay, v1 times 0 plus v2 is equal to 0. v2 is equal to 0. Let v1 be equal to 1, then v2 is equal to 1, 0. Hence, the solution becomes x of t, y of t is equal to c1, 1 minus 1, which is the v1 value, okay, the v1 vector, and lambda 1 is equal to 0, so E0 is equal to 1, plus C2 E of t, because this is in respect of t, times 1, 0. Okay, which is the second vector, or v2, corresponding for lambda 2 is equal to 1. It can be rewritten, x of t is equal to c1 plus c2 et. Okay, this is how you get x of t, and y of t is equal to c1 times minus 1 plus c2 et times 0, which is minus c1. Lambda 1 is equal to 0. This is a constant solution leading to equilibrium, so y1 of t is equal to c1. Lambda 2 is equal to 1 greater than 0, so the solution grows exponentially and diverges from the origin. So x of 2 is equal to c2 et. As c goes to infinity, x2 blows up, goes to infinity. Okay, so if you look at lambda 2 is equal to 1, it's greater than 0, so that's why the solution grows exponentially. It diverges. As we mentioned before, when lambda is greater than 0, this is what happens. Power series method. Power series are another approach to find solutions to differential equations. This is a common approach when elementary methods don't work. This approach assumes that the solution can be expressed as a power series around a point like x equals 0. A power series centered at x equal a is an infinite series of the form sigma n equals 0 to infinity cn times x minus a to the power of n is equal to 0 plus c1 times x minus a plus c2 x minus a times 2, or to the power of 2, plus etc. cn times x minus a to the power of n. An assumed solution of the form y of x is equal to sigma n equals 0 to infinity an xn is adopted. So we assume a solution of this form. Y of x is equal to sigma n equals 0 to infinity an x to the power of n. After adopting y of x is equal to sigma n equals 0 to infinity an xn, we need to find the first and second derivatives and replace them back into the original equation. So y prime of x is equal to sigma n equal 1, because we have shifted of one value up to infinity, and derivative of an xn is nan times x to the power of n minus 1. Y second of x is equal to sigma n equal 2 up to infinity, also another shift of n minus 1 times n times an times x to the power of n minus 2. Then we set the coefficient of each power of x equal to 0, and we solve the recurrence relationship to find the coefficients a of n. After that, we change the power of x in different derivatives from x to the power of n, or x to the power of n minus 1, or n minus 2 to m, so we can get rid of the x component. We can do that for the three of them by adjusting the index of the sum. This is why we can actually do that. Finally, we solve for an, or the an terms, to find the relationship between the an plus 1 and an, so the consecutive, or like the term that comes later, its relationship with the term that comes earlier. So we find the recurrence between terms at different indexes. As an example, for y of x, let m be n, so y of x is equal to sigma m equals 0 to infinity am xn. Here nothing actually changes. But for y second of x, we place m equal to n minus 2, then n equal to n plus 2. So looking back at y second, within this example here, we have an example which is y second minus y equal to 0. So y second of x is equal to sigma m equal minus 2. Why? Because n equals 0, so you replace n by m. So if n equals 0, then m starts with minus 2, because m is equal to n minus 2 up to infinity. N, which is m plus 2, times n minus 1, which is m plus 2 minus 1, or m plus 1, times an. A of n is a of m plus 2, correct, times x to the power of m, which is x to the power of n minus 2, since m is equal to n minus 2. Okay, So we replaced y and y second within this equation using this methodology. After that, we need to place y second, okay, and y of x within the original equation. So y second of x, second derivative, which is equal to m plus 2 times m plus 1, a m plus 2 x of to the power of m, and y of x, which is am xm, back in y second minus y equals 0. So m plus 2 times m plus 1 times am plus 2 minus y, which is minus am xm, is equal to 0. We factor out xm to the outside of this entire product. So you get am plus 2 is equal to plus am divided by m plus 2 times m plus 1. So for m is equal to 0, you get a of 2 is equal to a0 divided by 2. For m equal to 1, you replace m by 1. a3 is equal to a1 divided by 6. For m equal to a4 is equal to a2 divided by 12. a2 is a0 over 2, so which is a0 divided by 24. For m is equal to 3, a5 is equal to a3 divided by 20. a3 is actually a1 divided by 6, which is a1 divided by 120. So there's a recurrence between later and former components. Alright, now let's separate a0 terms and a1 terms. So let a equal a0 and b equal a1, because we notice that some of the terms depend on a0, like factors of a0, and other terms depend on a1. They are in dependency of a1. Y of x is equal to, of course, the form is sigma an x to the power of n, correct? Now, we need to split them because we have a0 and a1 separately. So let a be equal to a0 and b equal to a1. Hence, y of x is equal to a times all the terms that are dependent on a, which is a0, which is a2. a2 is a0 divided by 2, which is 1 over 2 factorial times a2 is also correlated with x squared, correct? an xn, remember. Plus, okay, what is the second term having a0? It is a4. So x to the power of 4 divided by 24, which is 4 factorial, plus etc. Plus b, the second term dependent on a1, times x, depending on the first condition, a1 is equal to 1, plus b times x plus a3 have a1 term, so plus x to the power of 3 divided by 6, which is 3 factorial, plus x5 times 1 over 120, which is 5 factorial. You notice the recurrence? So you have all the odd powers are multiplied by b, and all the even powers are multiplied by a. And this sequence, by the way, is cosh x, hyperbolic cosine x. The second one is sinh x, or hyperbolic sine x. Example, solve the following ODE using power series method. So we have y second minus x, y equals 0, y of 0 equal 1, y prime equals 0, the initial conditions. Y of x is equal to sigma n equals 0 to infinity an xn, y prime x equals sigma n equals 0 to infinity n xn minus 1, which is derivative of this quantity y of x, and y second of x is equal to n times n minus 1, which is this power, times an times x n minus 2. First we consider m equal n minus 2, then n equal m plus 2, in order to flip the power of x into m. We can do that because we can change the indices. So y second is equal to sigma m equal minus 2 to infinity. Why? Because m equal n minus 2. So if n starts from 0, m starts from minus 2 times n minus 1, which is n plus 1, am plus 2, because n equal m plus 2 times x to the power of m. Let m be equal to n plus 1, since y is going to be multiplied by x. This is for y of x. Okay, so we are done with y second. Now for y of x, since it is multiplied by x, then let m equal to n plus 1 or n equal to m minus 1. So once it is multiplied by x, it is rendered as x to the power of m again. Y of x is equal to sigma a m minus 1 x to the power of m minus 1, sigma m equal to 1 to infinity. we've gotten y second and y of x. We need to place them back into the equation. So m plus 2 times m plus 1 am plus 2x to the power of m minus x times y, which is am minus 1 xm minus 1 becomes x to the power of m once multiplied by x equals 0. So m plus 2 times m plus 1 times am plus 2 minus am minus 1 times x to the power of m equals 0. Therefore, am plus 2 equal am minus 1 divided by m plus 2 times m plus 1. Okay, now we start getting the terms. For m equals 0, a2 is equal to a minus 1 divided by 2. This term doesn't exist. There's no a minus 1. For m is equal to 1, a3, you simply replace m, is equal to a0, a1 minus 1 divided by 6. For m equal to a4 equals a1 divided by 12, m equals 3, a5 is equal to a2 divided by 20, etc. a2 also cannot exist because a2 is equal to a minus 1 divided by 2. For m equal 4, a6 is equal to a3 divided by 30, and a3 is a0 divided by 6. Okay, so you replace it back here, then you get a0 divided by 180. So the recurrent values are a0 and a1, and for the initial condition, a0 is equal to 1. Now, a1 is equal to 0. Why? Because a1 corresponds to the first derivative, and based on the initial condition, it is equal to 0. So you get y of x is equal to 1. Okay, 1 because it is a0 plus x3 divided by 6. Why? Because it is a3 times x3. a3 is a0 divided by 6 and a0 is 1. Plus x6, which is this term here, divided by 180, because why? a1 cancels out. All the terms containing a1 are 0. So you are left with all the terms containing a0. The first one being a0 equal 1, plus a3, which is a0 divided by 6, or x to the power of 3 times a0 divided by 6, or x3 divided by 6. Plus a0 divided by 180 times x to the power of 6. You see the 6 here, etc. Therefore, the limit equal to, if we run it for a6 and a3, which are x6 divided by 180, x3 divided by 6. Actually, a6 and a3 don't have the x within them. We've added it. So it is 1 divided by 180 over 1 over 6, which is 1 over 30. So it converges with time. Now for the radius of convergence, the inverse of the limit, which is 1 over L. So let's say this is a recurrent value. The radius of convergence would be 1 over 30. So around 30 for this term at least. Exercise 1 minus x squared y. Second derivative minus 2xy prime plus 2y is equal to 0 with initial conditions y0 equal 1 and y prime 0 equal 0. So y of x is equal sigma n equals 0 to infinity a n x to the power of n. This is y of x, standard form. Y prime is equal to the derivative of y of x, which is n a n x to the power n minus 1. Y second is equal to sigma n equal to infinity n times n minus 1 a n x to the power n minus 2. Expanding the equation, okay, so we've expanded to break it down to simple elements or simple components. So for y second, we let m be equal to n minus 2 to get rid of this power to turn it into x to the power of m. So n equal m plus 2, y second is equal to m equals 0 to infinity, m plus 2, which is n here, you replace n by m plus 2, times m plus 1, which is m plus 2 minus 1, times a m plus 2 times x to the power of n. For x2, y second, m equal to n, because the minus 2 component in the power will cancel out by the x squared. So for xy prime, let m equal n, xy prime is equal to sigma, m equal 1 to infinity, m x to the power of m minus 1 times x, which becomes x to the power of m. So for y, finally, m equal n, y equals sigma, m equals 0 to infinity, am x to the power of m. Then we place different components back into the equation, which is y second minus x squared y second minus 2xy prime plus 2y equals 0. So m plus 2 times m plus 1, am plus 2 xm, minus x squared y second, which is this one here, minus m times m minus 1, a to the index of m times x m minus 2 times x squared, which is x to the power of m, minus 2xy prime, which is minus 2. xy prime is mam, x to the power of m minus 1 times x, which reduces to x to the power of m. Finally, plus 2y, which is 2 times y is equal to am x to the power of m equal 0. We factor out and you get am plus 2 is equal to m squared plus m minus 2 divided by m plus 2 times m plus 1 am. Okay, so we start with the terms. For m equals 0, a2 is equal to minus a0. Then m equal 1, m equal 2, a4 is equal to, you replace m by 2, you get 4 divided by 12, a2, equal minus 1 divided by 3, a0. M equals 3, a5 is equal 10 divided by 18, a3 equals 0. So all the odd indices are 0. This is the conclusion. M equal 4, a6 equal 18 over 30, a4, which is minus 1 divided by 5, a0. Here you notice something. For each index, let's say a6, it should be even at first, is equal to minus a0 divided by the index minus 1, which is 6 minus 1 or 5. Hence, y of x is equal to minus 1 plus x4 divided by 3 plus x6 divided by 5 plus xa divided by 7, etc. with all the odd elements null because they depend on a3, which is 0. And the value of a0, we took it from this initial condition, which is y of 0 is equal to 1. So a to n is equal to 1 divided by 2n minus 1. And also for the first derivative, y prime of 0 is equal to 0. So the second or the first derivative for which the second index, all values are 0. Finally, limit and radius of convergence. The limit of this series is equal to limit, when n goes to infinity, of an plus 1 divided by an, equal limit n to infinity to n minus 1 divided by 2 times n plus 1 minus 1, which we took it from the previous equation. You have a to n is equal to 1 divided by 2n minus 1. So is equal to limit n goes to infinity to n minus 1 divided by 2n plus 1, which is equal to n divided by 2n or 1. Then the radius of convergence is the inverse of the limit, which is equal to r equal 1 divided by L equal 1. Laplace transform. Laplace transform is a powerful integration transform used to solve differential equations. Let f of t be a real or complex function defined for t greater than equals 0. The Laplace transform denoted by f of s or L f t is given by L f t equal f of s equal integral from 0 to plus infinity e minus st f of t dt, where s is a complex number of the form alpha plus I omega, where alpha is the real part and omega is the imaginary part. Of course, the integral must converge. And also another note, here we are transferring from t to s, like we are switching domains, just like the Fourier transform switches from the time domain into the frequency domain. Laplace transform properties. At first you have linearity. LAFT plus BGT is equal to AFS plus BGS, which means that the transform of a sum is equal to the sum of the transforms. First derivative, LF prime of t is equal to SFS minus f of 0. Okay, these are very important, they come in handy. Second derivative, LF second of t is equal to s squared fs minus sf0 minus f prime 0. Nth derivative, so LFNT is equal to s to the power of n fs minus sn minus 1 f0 minus, that would be a sequence all the way to minus fn minus 1, 0. Integration in time domain, L integral 0 to t f tau d tau equal to f of s over s. Time shifting, so L ft minus a, ut minus a, which is the step function Heaviside, we will see it later in this course, is equal to exponential minus as times f of s, where ut minus a is the Heaviside unit step function. Frequency shifting LEAT ft is equal to fs minus a, and scaling LFAT is equal to 1 divided by a f of s divided by a, where a is greater than 0. Convolution theorem. So L of f times g, which is f convoluted with g, t, is equal to fs dot gs times gs, where f g t, this is what the convolution means, it is equal to integral of 0 to t f tau times g of t minus tau. So g has a time shift from f d tau, okay? Initial and final value theorems. So limit ft where t goes to 0 plus is equal to limit s goes to infinity sfs. Limit ft t goes to infinity is equal to limit s goes to 0 sfs. Okay, so you invert the limits. Inverse Laplace transform is the process to transition back from the frequency domain s into the time domain t, which is denoted by L minus 1 f of s is equal to ft, which is equal to 1 divided by 2 pi I being the imaginary complex notation, integral from gamma minus I infinity to gamma plus I infinity est times f of s ds, or L minus 1 f of s, where gamma is a real number and I is equal to square root of minus 1. Of course, it's going to become much clearer in the next slides. So considering fs and f of t, this is a table that you need to count on in order to find the inverse transform or the transform. So 1 over s is the transform of 1, t, the transform of t is 1 over s squared, or let us place them, let us go from left to right. So n factorial divided by s to the power of n plus 1 is equal to t to the power of n. 1 over s plus a is equal to exponential minus at. Omega divided by s squared plus omega squared is equal to sine omega t in the time domain. L minus 1 s squared minus omega squared divided by s squared plus omega squared is equal to cosine omega t minus omega t sine omega t. Here on the next side, s over s squared plus omega squared is cosine omega t, and the inverse transform s plus a divided by s plus a squared plus omega squared gives us e minus at cosine omega t. Omega divided by s plus a squared plus omega squared gives us e minus at sine omega t. So you need to identify these terms, omega and a, to find what would be the time transform, what would be the result of the inverse transform. L minus 1 of 1 divided by s squared plus omega squared 2 is equal to t sine omega t divided by 2 omega. L minus 1 s divided by s squared plus omega squared equal t cosine omega t divided by 2. This is another table. It mostly have all the things that we've seen before, so you can take a picture of it as a reference. This is how you'll be able to find the inverse Laplace transform or the transform itself. Example: fs is equal to 1 divided by s squared plus 4. Find f of t using Laplace inverse transform. You can pause the video, go back to the table, which is the reference table for different transforms, and try to figure it out yourself. Now, the known form that is the closest to fs is omega divided by s squared plus omega squared. Omega in such case would be 2, so 2 squared is equal to 4. Except we don't have 2 in the numerator. We simply multiply both the numerator and the denominator by 2, and this way we don't change the value of fs, but at the same time we get fs in the form of omega divided by s squared plus omega squared. So L minus 1 from the table, the transform of omega divided by s squared plus omega square is equal to sine omega t. Hence, w equal to, we need to multiply the numerator by 2 to match the form and also the denominator as well to avoid changing the value. So you get 1 divided by 2 times 2 divided by s squared plus 4, which is 2 squared, with omega equal 2 in this equation. Then the Laplace inverse transform, which is ft or L to the power of minus 1 fs, is equal to 1 divided by 2 sine omega t, which is sine 2t. Another one, fs equal 5 divided by s plus 2 squared. Find ft using Laplace inverse transform. Okay, you can pause the video and try to solve it at first. The standard form is L minus 1 of 1 divided by s plus a n equal to t to the power of n minus 1 divided by n minus 1 factorial e minus at, for n is within n, natural numbers. Okay, so we notice something, that s plus 2 square is like s plus a to the power of n equal 2 and a equal 2. Now for the numerator, you simply multiply by 5. So you multiply the inverse transform or the transform at first by 5, then you can convert it to t to the power n minus 1 divided by n minus 1 factorial e minus at. So n equal 2, a equal 2, hence f of s is equal to 5 times 1 divided by s plus 2 square. The inverse transform becomes 5t e to the power of minus 2t, which is t to the power of 1 times e minus 2t divided by 1, or 1 factorial, which is 1. Another one which is a little bit more complex, fs is equal to 2s plus 5 divided by s squared plus 4s plus 13. Okay, so the standard form is s squared plus 2 square. Okay, so s squared plus 4s plus 13 is equal to s plus 2 square and plus 9, which gives you 13. This form is also familiar if you look back to the table. This looks like fs is equal to 2s plus 5. Of course, here it is not familiar, but the denominator is s plus a square plus omega square, a equal 2 and omega equal 3. So this is the form s plus a divided by s plus a square plus omega square, or omega divided by s plus a square plus omega square, or both of them, since we have s and a number. Okay, we have 2 times s, so s plus a can be accounted for, and a is equal to 2, then you factor out 2 here, so you get 2 times s plus 2, and what remains is 1. Let's check it out. At first, a equal 2 and omega equal 3. So we need to break down this equation or this fraction. F of s can be broken down into 2 times s plus 2 divided by this denominator plus 1 over 3 divided by s plus 2 square plus 9. Okay, why? Because you need omega in the numerator here. We don't have omega, we still have 1, which is 2s plus 2 is 2s plus 4 plus 1, you still have 1. Okay, so in order to get it into the form of omega divided by s plus a square plus omega square, so you multiply by 3, which is omega, and you divide by 3 so that we won't change the value of the second component. Hence, this becomes 2 times s plus 2 divided by s plus 2 square plus 9, which is e minus at cosine omega t, with a equal 2, omega equal 3. So 2 exponential minus 2t cosine 3t plus 1/3, and this is omega divided by s plus a square plus omega square, for which omega equal 3, a equal 2. Hence, this becomes 1 divided by 3 e minus 2t sine 3t with a equal 2 and omega equal 3. Another one, fs is equal to s plus 5 divided by s squared plus 4s plus 5. Okay, so s squared plus 4s plus 5 can be broken down into s plus 2 squared plus 1, where a equal 2 and omega equal 1. These are the forms that are compatible with this equation. So let's break it down. Now the numerator can be broken down into 2 times s plus 2 and plus 1 to the other side. So f of s is equal to 2 times s plus 2 divided by s plus 2 squared plus 1 plus 1 divided by s plus 2 squared plus 1. Okay, so omega is equal to 1, which is compatible, and a is equal to, and here you multiply by 2 on the outside. Then the inverse Laplace transform becomes 2 times the transform of the first part is e minus at cosine omega t, which is e minus 2t cosine t, because a equal 2, omega equal 1, plus e minus 2t sine t, which is the transform of the second part, or 1 divided by s plus 2 squared plus 1 with omega equal 1 and a equal 2. We can factor out e minus 2t and get f of t is equal to e minus 2t times 2 cosine t plus sine t. fs equal 1 divided by s plus 3 squared. Again, find f of t using Laplace inverse transform. So what is the form? The form is 1 divided by s plus a to the power of n. The inverse transform of this quantity gives you back t to the power of n minus 1 divided by n minus 1 factorial e minus at. So what is n? N is actually 2 and a equal 3. The final answer would be t 2 minus 1, which is 1 divided by 1 factorial, e minus at with a equal 3, so t exponential minus 3t. fs equal 4 divided by s squared plus 16. Now this one looks familiar. It looks like s squared plus a squared with a equal 4. And let's check if a is available in the numerator in such case. So the form is omega divided by s squared plus omega squared. Omega is 4, which is completely compatible with f of s. So the transform, or the inverse transform rather, gives you back sine omega t with omega equal 4. Hence, the solution for this one is f of s is equal to 4 divided by s squared plus 4 squared, and f of t is Laplace inverse transform of 4 divided by s squared plus 16 equals sine 4t. fs equal s plus 2 divided by s plus 1 squared plus 1. Here you can immediately identify that we have a and omega, a equal 1, omega equal 1. Now for the numerator, it needs to be broken down into simpler pieces. So the general form is s plus a divided by s plus a squared plus omega squared equal e minus at cosine omega t. L minus 1 omega divided by s plus a squared plus omega squared equal e minus at sine omega t with a equal 1 and omega equal 1. So s plus a would be s plus 1. What remains is 1, which is also equal to omega. Hence, the final solution becomes, at first, f of s can be broken down into this form, s plus 1 divided by s plus 1 squared plus 1, compatible with the first argument, plus 1 divided by s plus 1 squared plus 1, compatible with the second argument, which is of the form omega divided by s plus a squared plus omega squared, where a is equal to 1 and omega equal to 1. So the final inverse transform is equal to e minus t cosine t plus e minus t sine t. Convolution theorem. This is mostly used in applications such as DSP, digital signal processing. If f of s is equal to L f of t and g of s is equal to L g of t, then the Laplace transform of their convolution product is equal to fs gs, is equal to the product of the two Laplace transforms of f and g respectively, where the convolution is defined by, what is the convolution? It is the integral from 0 to t f of tau times g of t minus tau, which is a time shift from f, d tau. Okay, g t minus tau is shifted by 1 tau to the right from f. So t minus tau equals 0, then t is equal to plus tau. In other words, g is distant of 1 tau to the right of f of t. An example for that, let's say e of s is equal to 1 divided by s times s plus 1. Find the solution using the convolution method. Okay, so e of s can be broken down into two components. F of s is equal to 1 divided by s, and g of s equal 1 divided by s plus 1. Okay, so f of t is equal to L minus 1 f of s, which is 1, and g of t is equal to L minus 1 g of s, which is e minus t. These are the respective inverse Laplace transforms for f of s and g of s, based on the table, of course. Then, the convolution product, ft f or fgt is equal to integral 0 to t ft times g t minus tau, actually f tau times g t minus tau d tau. Okay, which is equal to integral from 0 to t, the first element, which is f of t, which is 1, times e minus t minus tau. Okay, here you need to create a time shift. So you replace t by t minus tau, d tau. We are integrating in respect of tau, which gives us e minus t, which is the constant here, okay, because you get e minus t times e plus tau, okay. So e minus t integral from 0 to t, e tau d tau, then e of t is equal to e minus t e tau between t and 0, or 1 minus e minus t. So the inverse Laplace transform of this es is equal to 1 plus e minus t. Another exercise to sharpen you in this concept of convolution theorem. Let's say we have a function e of s is equal to 1 divided by s times s squared plus 1. At first, we need to break the components down from e of s to f of s and g of s. Okay, so you get fs equal 1 divided by s and gs equal 1 divided by s squared plus 1. We need to find the transforms or the inverse transform for both components, fs and gs, to make them ft gt. This is the first step before evaluating the convolution product. So g of s actually can be compared or matched by the form omega divided by s squared plus omega square, I think, but doesn't matter. So omega is equal to 1, and hence we can transform it immediately to the form, to its convenient inverse transform based on the table. And for 1 of s, L minus 1 of 1 give us 1 over s. So the inverse transform of the first component is simply 1. Then L minus 1 sine t is the one for 1 divided by s squared plus 1. So the inverse transform of 1 divided by s squared plus 1 is equal to sine t. Okay? Hence, now let's get the convolution product. Okay, actually, this is written incorrectly. The Laplace transform, not the inverse one. The Laplace transform of 1 gives us 1 divided by s. Laplace of sine t gives us 1 divided by s squared plus 1. The inverse of these two, 1 over s and 1 over s squared plus 1, the inverse transform of them respectively give us back 1 and sine t. So the convolution product is equal to integral from 0 up to t of 1 times sine t minus tau. Remember, here you need to change t to t minus tau d tau. Okay, which is cosine t minus tau between t and 0 equal 1 minus cosine t. Hence, the inverse transform of 1 divided by s times s squared plus 1 is equal to 1 minus cosine t. So here we have the direct transform, not the inverse. Here we have the inverse transform. The direct transform gives you s components or s elements, and the inverse transform gives you back the t function, or the function that is based on t. Exercise: find the solution using the convolution method for the following equation. E of s is equal to 1 divided by s squared times s plus 2. You can pause the video and try at it yourself first. So let's move on. F of s is equal to 1 divided by s squared, that's the first thing that we notice, and g of s is equal to 1 divided by s plus 2. This is how you can break it down easily. Okay, for the first argument, so looking back at the table, the standard forms to use are the following. L minus 1 of 1 divided by s to the power of Sn, which is for f of s, is equal to t to the power n minus 1 divided by n minus 1 factorial, for n greater than 0, of course. And for the second form, it looks like 1 divided by s plus a or s minus a. So it is equal, the inverse transform is equal to e to the power of a t. Okay? So, but here a is negative. So you simply multiply by minus. And again, you have a equal to and n, which is the power, is equal to 2 for the s squared. So L of t is equal to 1 divided by s squared, that's Laplace transform for t, and L of e minus 2t is 1 divided by s plus 2t. Hence, the inverse transforms would be the following: t and e minus 2t. So let's integrate. This is f of t, this is g of t. So the convolution product would be integral from 0 to t, f of t, which is tau. Okay, you replace t by tau again for the first one. And for the second one, which is e minus 2t, you replace t by t minus tau. So e minus 2 times t minus tau d tau is equal to e minus 2t. You bring it to the outside of the integral. Integral from 0 to t, tau times e to tau d tau. Here you have a product. So you need to integrate by part. Let u be equal to tau, then du equal 1 d tau, dv equal e to tau, then v is equal to 1/2 e to tau. So integral of u dv is equal to uv minus integral v du. Fgt is equal to e minus 2t times 1/2 tau e to tau between t and 0, which is uv minus 1/2 integral 0t e to tau d tau, which gives you e minus 2t times 1/2 t e to t minus 1 divided by 4 e to tau between t and 0. And the final result becomes t divided by 2 plus 1 divided by 4 e minus 2t minus 1 divided by 4. Discontinuous inputs and Heaviside. Discontinuous inputs are modeled using the Heaviside unit step function, denoted as u of t minus a being the time-wise shift, used so often, by the way, in DSP. The definition of a step function u is given by u of t minus a is equal to 0 for each t less than a and 1 for each t greater than or equal to a. So in other words, the transition based on this graph below from 0 to 1, which is a drastic hardline transition, is performed at t equal a from 0 to 1. After a, all of the values are 1, and before it, all the values are 0. Now, for a step function as u of t, which doesn't have an a, the transition starts at 0, at t equal 0 instead of t equal a. Laplace transform of the Heaviside function. By the way, the unit step function is also called echelon signal. So L of ut minus a is equal to e minus as divided by s. That's Laplace transform of ut minus a. If you multiply a function by a shifted unit step u, such as L ft minus a ut minus a is equal to, this Laplace transform becomes e minus as fs, where fs is equal to the Laplace transform of f of t. Example, the Laplace transformation for a step function shifted 3 to the right. 3 to the right means ut minus 3. Why? Because for t minus 3 is equal to 0, t equal plus 3. Then fs, which is the Laplace transform, becomes L ut minus 3 equal e minus 3s divided by s. Find the Laplace transform for the following function. At first here we can notice, based on the graph, that at least we have one step function, which is u t minus 2, that flips from 0 or transitions from 0 to 1 at t equal 2. But we also have another one, which is ut minus 6, except it is becoming 0 after 6. So what's happening? What's happening is that we are subtracting ut minus 2, or ut minus 6 rather, from ut minus 2. Okay, the second function, which is the blue one, is ut minus 6, shifted 6 quadrants to the right. It turns to 1 at t equals 6. First one is ut minus 2 shifted 2 to the right, which is this one in purple. For t minus 2 equals 0, then t equal 2. The overlap that you see in the graph above is the byproduct of subtracting the second step function from the first, which gives you ut minus 2 minus ut minus 6. Okay, so since after 6 ut minus 6 is equal to 1, 1 minus 1 is equal to 0. So the two values subtracted give us only the window from 2 to 6, which is equal to 1. This is also called a port signal. So let's find the Laplace transform for this function, which is ut minus 2 minus ut minus 6. Fs equal Lut minus 2 minus ut minus 6, which is the transform of each of the functions. So Lut minus a is equal to e minus as divided by s, and you can apply it for both sides. Okay, then f of s is equal to e minus 2s divided by s for ut minus 2 minus e minus 60 divided by s, which is for ut minus 6. Equal also, we can simplify it by e minus 2t minus e minus 60 divided by s. Laplace transform for this function. Find the Laplace transform for the following function. F of t is equal to 0 for t greater than equal to 0 less than 2, and t minus 2 for t greater than equal to 2. At first we need to express f of t as Heaviside, then we need to find the Laplace transform. Okay, what does it mean expressing f of t as Heaviside? You see, f of t, which is t minus 2, usually has infinite values. It is a line, an equation of a line. But here, in this unique case, it is only valid for t greater than or equal 2. So before t equal 2, this line has 0 values. It doesn't even exist. So how to actually limit this line or confine it within a window starting from t equal 2? You need to multiply it by the step function, the unit step, with a shift of t equal 2, which is ut minus 2. So f of t is equal t minus 2 multiplied by ut minus 2, which gives you the graph that you see to the top left. Okay, now finding the Laplace transform. So L f of t ut minus 2 equal f of s multiplied by e minus as. So let u equal t minus 2. Here we are changing the variables. Then L f of t is equal integral 0 to infinity f of t e minus st dt. Alright, so we change the variables from t to u. Supposedly u equal t minus 2, and this u is not the unit step function, by the way. It is only a supposed variable. So L f of t is equal to integral 0 to infinity f of t e minus st, which is equal to integral 0 to infinity u e minus s u plus 2 du. Okay, so u equal u and du equal 1. So here we changed from t to the s domain. Okay, so the transform is integral 0 to infinity u e minus s times u plus 2, because t is changed into u plus 2. Okay, let us suppose that capital U, to distinguish it from small u here, is equal to u, du equal 1, dv equal e minus s u plus 2, and v equal minus 1 divided by s e minus s u plus 2. This is the variable change, actually, in the integration by parts. Okay, integral u dv is equal to uv minus integral v du. So L of minus u divided by L equal minus u divided by s e minus s u plus 2, which is u times v, minus integral between 0 and infinity v du, which is minus 1 divided by s e minus s u plus 2 du. Okay, so we got the transformation of Laplace for the components, and we are integrating from 0 to infinity. Okay, so next L equal minus u divided by s e minus s u plus 2 0 to infinity minus integral 0 to infinity minus 1 divided by s e minus s u plus 2 du. Okay, so equal minus u divided by s e minus s u plus 2 minus 1 divided by s square e minus s u plus 2 from infinity to 0. Okay, so we've done another integration by parts over here, which gives us 0 minus 1 divided by s squared e minus 2s equal 1 divided by s squared e minus 2s. I hope it is clear. It is integration by parts, okay? Except we've done it into multiple stages. Okay, thank you for watching. That's all for this presentation. Hope you had fun with it, and see you next time.